A phenomenon currently observed within Earth's atmosphere presents a profound scientific puzzle. 3 Atlas, an interstellar visitor traversing our celestial neighborhood, exhibits movement and activity that fundamentally defy established physical principles. This object generates powerful jets of ejected material, yet lacks the essential gaseous components necessary to power such phenomena. Observing its behavior feels akin to witnessing a high-speed vehicle accelerate along a roadway despite possessing no engine within its chassis. For an extended period, astronomers held the assumption that their instruments might be insufficient, believing that more advanced technology would eventually illuminate the underlying mechanism. Instead, the most recent spectral analysis, conducted on the 15th day of November in the year 2025, has significantly intensified the mystery. The data obtained does not merely challenge conventional comet physics, it opens conceptual pathways that remain largely unvoiced within the scientific community. The ramifications extend far beyond the study of this single anomalous celestial body, potentially reshaping our understanding of unseen entities drifting through the vastness of space. Should this sense of profound curiosity resonate with you, a pull towards unresolved cosmic questions, this narrative invites continued exploration. The following investigation delves deeper into the implications, which touch upon the very nature of what might exist beyond our current detection capabilities. On the night following the 15th day of November in the year 2025, a dedicated group of amateur astronomers operating from the Canary Islands directed their observational equipment towards an object that, based on existing knowledge, should not exist in the manner it was being observed. Their initial intent was not to seek revolutionary findings, but rather to perform another routine spectroscopic examination of 3 Atlas, the interstellar traveler that had been persistently observed within our solar system for several months. This visitor had already captured attention due to its distinctive pale emerald radiance and its highly unpredictable behavioral patterns. The astronomers carefully tuned their spectrometer to observe wavelengths spanning from 628 nanometers down to 88 nanometers, a range commonly employed for studying cometary bodies. While possessing relatively low resolution, the configuration was undeniably sound from a scientific standpoint, designed to gather valuable data that could fill existing knowledge gaps, corroborate established understanding, and potentially reveal intriguing phenomena under favorable circumstances. The resulting spectrum, however, defied all expectations. Instead of the anticipated complexity, it presented an unnervingly smoothness. Profoundly, almost impossibly smooth. The data revealed a gentle, unbroken descent towards the red end of the spectrum, conveying a singular, stark narrative: dust alone. No distinct peaks marked the presence of gases. No valleys indicated absorption features. No unique molecular signatures were detectable. Only the silent, uniform murmur of sunlight diffused by trillions of infinitesimal particles remained. Anyone familiar with the typical spectrum of a comet situated at a similar distance from our star would recognize this absence as fundamentally anomalous. It was profoundly incorrect. A normal comet under these conditions should blare forth signals of intense activity. One would anticipate the distinct signature of cyanogen molecules near 388 nanometers, though it was acknowledged this specific wavelength lay just beyond their current observational window. Even so, some measurable indication was expected, perhaps the faint echo of volatile compounds vaporizing from the comet's exposed surface, a subtle suggestion of the chemical tumult that animates these celestial wanderers. Instead, the data offered nothing, merely the reflection of light off a lifeless rock adrift in the cosmic void. The research team immediately conducted rigorous calibration procedures. They directed their instrument towards the brilliant star Vega, measured the well-known H-alpha line within its spectrum, and confirmed their apparatus was functioning with perfect precision. They re-examined the archival atlas data for corroboration. The results remained unchanged. Well, nearly unchanged. Scattered across the otherwise featureless continuum, approximately 30 minuscule, almost imperceptible peaks appeared, faint undulations that might superficially resemble meaningful signals to an inexperienced observer. However, these subtle anomalies were conclusively determined to be spurious, mere artifacts, not genuine cosmic signatures. In the realm of astronomical observation, certain signals are dismissed as mere background noise, statistical anomalies inherent to any precise measurement. Astronomers, particularly those working at the extreme edges of their instrument's capabilities, become adept at recognizing these random fluctuations. They resemble the human tendency to perceive familiar shapes, like faces in clouds. While intriguing, they typically signify nothing substantial. From the recorded spectrum, this principle led to a specific interpretation regarding the object designated 3 Atlas. The data indicated that 3 Atlas was effectively inert, a lifeless celestial body reduced to a mere aggregate of dust. Crucially, it possessed neither gas nor volatile compounds nor any signs of ongoing chemical activity. Dramatically, one could describe it as the skeletal remains of a comet. Such an entity might, under the relentless pressure of sunlight, generate a faint, diffuse dust trail. However, it was unequivocally not capable of producing significant phenomena.
There were no jets, no outbursts, and no sudden, unpredictable changes in brightness. Its anticipated path foretold only a quiet, predictable progression through the inner regions of our solar system, before its inevitable return to the profound darkness between the stars. Yet this seemingly straightforward narrative encountered a profound contradiction. Less than 24 hours after the spectrum was captured, 3 Atlas underwent a dramatic transformation. The object decisively reactivated. Observations made by the SLU telescope network subsequently revealed compelling imagery. The previously quiescent body was now encircled by brilliant, sharply defined plumes of ejected material. 3 distinct jets, exhibiting perfect symmetry and immense power, erupted forth, blasting copious amounts of dust and other debris into the surrounding space. The intensity of this activity matched expectations for a comet experiencing a full-scale eruption. This represented a startling reversal of fortune. The very same object that, moments earlier, had spectroscopically registered as completely dead and lifeless was now behaving with the exuberance of a celestial partygoer, seemingly awakened from a prolonged slumber to initiate a grand celebration. It is precisely at this juncture, confronted with such a striking and seemingly impossible reversal, that astronomers often resort to using words they would prefer to avoid. Terms like impossible and contradictory become unavoidable descriptors in the face of such compelling evidence. The underlying logic governing cometary behavior follows precise scientific principles. Within comet physics, distinct rules dictate the formation of jets. These powerful jets necessitate the presence of volatile materials. When exposed to solar heat, these volatiles transform into gas. This gas, in turn, reliably manifests within spectral analyses. This sequence represents a chain of cause and effect as dependable as the force of gravity itself. It is fundamentally impossible to observe structured, powerful jets without the specific chemical processes driving them. Observing such an occurrence feels akin to witnessing a high-speed vehicle traverse a highway at a velocity of 70 miles per hour, yet its fuel gauge stubbornly indicates an empty tank and no engine operates beneath the hood. Some individuals may recall the first confirmed interstellar visitor to our solar system, designated Oumuamua, which passed by our planet in the year 2017. This particular object also presented a featureless spectrum during observation. No detectable gas emissions, no obvious volatile compounds were identified. However, a critical distinction existed regarding its behavior. Oumuamua did not exhibit typical cometary activity. Instead, it tumbled erratically through space. It experienced a slight acceleration at times, a phenomenon whose precise cause remains partially unresolved to this day.
Crucially, it never generated jets, never developed a surrounding coma, and never displayed the characteristic green glow associated with comets. While undoubtedly strange, Oumuamua behaved consistently within its own peculiar framework. Researchers found they could construct models capable of explaining the majority of its observed behavior, even if those models challenged conventional understanding for certain astronomers. The situation with 3I Atlas, however, presents a starkly different scenario. 3I Atlas exhibits what appears to be a split personality. For periods encompassing half its observable cycle, it appears utterly inert. For the remaining half, it transforms into one of the most dynamically active objects currently visible in the celestial sphere. It resembles the sudden flipping of an unseen switch by another observer, except no switch mechanism exists. No physical explanation currently accounts for this dramatic shift. The spectral data unequivocally indicates the engine-generating activity is powered off. Simultaneously, the physical evidence of the powerful jets demonstrates it operating at full capacity. Astronomers now confront a phenomenon entirely unprecedented in their collective experience. An entity exhibiting the uncanny appearance of life, yet revealing a lifeless signature under spectroscopic analysis, stands as a profound enigma. This visitor, originating from beyond our solar system, defies the very scientific principles humanity has meticulously established over centuries. As astronomers scrutinize its presence, a cascade of increasingly complex questions emerges. The fundamental problem arises from a stark contradiction. If the spectroscopic data accurately reflects reality, the existence of its powerful jets should be impossible. Yet the jets themselves are undeniably real phenomena, visually confirmed and compelling in their undeniable presence. This forces a sobering conclusion. A significant element of the universe's behavior is escaping our current models. Something fundamental is occurring, operating outside the parameters of any known class or category we have constructed. Consequently, the essential query reverberates through the scientific community. What truly lies before us? Is this the cosmos revealing an entirely new branch of physics previously unimagined and unmodeled? Or is it fundamentally something beyond our current comprehension? For at this juncture, the gathered evidence presents two mutually exclusive narratives. Logically, both cannot simultaneously represent objective truth. Unless, and this is the most unsettling possibility, we have fundamentally misunderstood the nature of the inquiry itself, asking the wrong questions all along.
The mere existence of these jets, capable of activation without the presence of gas, without thermal energy, without any of the conventional triggers known to physics, renders the next question inescapable. What is the actual mechanism governing their behavior? This leads directly to the subsequent chapter, the enigmatic reappearance of the jets, a phenomenon described as either a miraculous event occurring within a single day or the manifestation of a profound and unknown mechanism.
The crucial observational data arrived precisely at 6:10 in the morning, according to Universal Time, on the 16th day of November. The Canary 1 telescope, a key component of the SLU network, transmitted the imagery of the three-eyed Atlas celestial body with remarkable clarity and high contrast. There they were, captured in the image, vivid, unmistakable, and symmetrically structured plumes emanating directly from the central nucleus. These plumes extended away like the perfectly balanced arms of a geometric pinwheel. They were not disordered sprays of dust nor irregular bursts of matter, but rigidly structured jets, possessing an almost artificial precision, reminiscent of lines drawn with an exact ruler. 3 distinct jets, spaced with mathematical regularity, each maintaining its own distinct and coherent form as it expanded outward into the vastness of space.
Such artificial regularity compels prolonged scrutiny. It triggers a visceral reaction for any observer conditioned by years of studying cometary behavior, instinctively signaling a profound anomaly that disrupts ingrained patterns of understanding. When encountering such unnatural symmetry in nature, scientific reasoning narrows the possibilities down to 2 primary explanations. Either the structure has been sculpted by highly specific and powerful physical constraints, such as dominant magnetic fields or precise rotational dynamics acting upon the object, or its form suggests deliberate design and construction. Given our current understanding of the universe, the notion that comets are engineered artifacts is generally dismissed. This forces a desperate search for a plausible natural mechanism capable of producing such an effect. However, the established models of cometary activity consistently fail to provide an adequate explanation for this particular observation. Crucially, no thermal trigger was identified. 3I Atlas was not situated in its orbit where solar heating is most intense. It had not experienced a sudden, dramatic increase in solar radiation. It was also not undergoing any obvious rapid change in its spin or orientation that would expose fresh, highly volatile, rich patches of its surface to direct sunlight. The object simply existed on its trajectory, coasting inertly through space, defying expectations for an active comet. Despite maintaining a consistent distance from the Sun and the same illumination angle as it had for several days, something remarkable occurred between the night of November 15th and the morning of November 16th. Initially, the comet's spectrum revealed a period of complete inactivity. However, within hours, jets began to erupt, only to cease again a few days later and then resume once more. This erratic on-off pattern was unprecedented in the study of cometary behavior. Unlike artificial light bulbs, comets do not typically switch their outgassing on and off in such a manner. Once a comet begins to outgas, it generally persists until it exhausts its accessible volatiles or moves sufficiently far from the Sun, causing temperatures to drop. Variations in intensity can occur due to the rotation of the nucleus, with different faces of the comet facing the Sun at various times, leading to fluctuations in activity. Nonetheless, complete shutdowns followed by immediate reactivations on such short timescales had never been observed before. This pattern did not align with the typical behavior of sublimation processes. Some researchers began to consider the possibility of periodic behavior. Perhaps the comet, designated 3I Atlas, had an unusually short rotation period, causing the jets to fire only when specific regions faced the Sun. However, upon closer examination, the timing did not match any consistent rotational period.
The activity cycles did not follow a regular pattern, ruling out periodicity. Instead, the behavior seemed reactive, as if the comet was responding to an external stimulus. Yet no one could determine what exactly it was responding to. Another hypothesis suggested internal energy sources. Some scientists proposed that there might be a chemical process occurring within the nucleus, generating energy that drives the jets independently of solar heating.
This idea emerged as researchers sought to explain the comet's unpredictable and seemingly autonomous activity. Despite these theories, the true mechanism behind the comet's erratic behavior remained a mystery, challenging existing models of cometary physics. The central scientific puzzle surrounding this enigmatic object remains its complete lack of expected physical signatures. Crucially, instruments detect no infrared excess, a phenomenon typically revealing internal heat sources within celestial bodies. Furthermore, no anomalous radio emissions have been registered, which might otherwise hint at complex chemical processes occurring beneath the surface. Equally perplexing is the absence of any detectable temperature increase preceding the dramatic outbursts themselves. For the vast majority of its orbital journey, the object appears utterly inert, exhibiting all the thermal characteristics of a lifeless remnant, until abruptly it commences ejecting substantial material into the void of space. It is important to note that dust-only jets are not entirely unknown within the realm of cometary science. Astronomers have indeed observed such phenomena before. When the force exerted by solar radiation pressure becomes sufficiently intense, or when powerful electrostatic fields develop, it is theoretically possible to dislodge fine dust particles from a comet's surface. This process can occur without the direct involvement of escaping gases to carry the particles away. However, these naturally occurring jets possess distinct limitations. They are characteristically weak, their structure is diffuse and unstable, and they manifest visually as only faint streaks against the background of space. Significantly, they do not exhibit the dramatic on-off behavior witnessed with this particular object. They certainly lack the precise, valve-like switching observed. This profound discrepancy is where the scientific conversations become intensely intriguing. These discussions, however, are unfolding primarily outside the formal channels of published research, in the realm of private correspondence between astronomers and during late-night video conferences linking observing teams. Within these informal exchanges, scientists are cautiously employing terminology that borders on the artificial, using phrases such as controlled venting and coordinated release. It is vital to understand that this language is not born from the conviction that the object is artificial or constructed. Rather, these specific terms are emerging organically because they represent the only vocabulary that accurately describes the bizarre, precisely timed behavior of the jets. The jets appear to be managed, exhibiting an internal mechanism that seemingly opens and closes, releasing material in measured bursts rather than the continuous outgassing typical of natural cometary activity. This observation is fueling growing interest in the possibility of a hidden, complex internal structure within the object. The prevailing hypothesis is shifting. Perhaps the object designated 3I Atlas is not a solid monolithic nucleus, as comets are traditionally understood to be. Instead, mounting evidence suggests it might resemble a rubble pile, a loosely aggregated collection of numerous fragments held together primarily by their own weak mutual gravity. Within this structure, extensive voids and cavities could exist, potentially explaining the unusual and seemingly controlled manner in which material is expelled into space. If these cavities, through their ability to trap pressure and gradually amass it, were suddenly to discharge their pent-up force, the result might resemble the jet-like phenomena we observe. Nevertheless, even this model has its limitations, particularly when it comes to explaining the symmetry of the jets. The formation of 3 evenly spaced jets from randomly distributed cavities within a pile of rubble is highly improbable. One would expect a chaotic and unordered pattern instead. This leads us to contemplate an object that behaves as though it possesses mechanical intricacies, internal processes that are initiated and halted at will, and a system that reacts to unknown conditions in ways that defy our predictive capabilities. The jets themselves, while intriguing, are not the primary enigma. We have a reasonable understanding of jet formation. The main concern lies with the unpredictability of their occurrence. The jets can vanish entirely, rendering the object seemingly lifeless, only to re-emerge after several hours, as if the comet had merely paused in its activities. This is not the typical behavior of a comet. It suggests something beyond our current comprehension. But there is more to this phenomenon than just the jets. They are merely the most conspicuous anomalies.
The soft emerald light radiating from the comet's coma, reminiscent of bioluminescence in the depths of dark waters, is a testament to the natural wonders that such celestial bodies can display. The underlying cause of this persistent chromatic phenomenon is now understood to originate from a specific molecular process. The characteristic green luminescence occurs due to diatomic carbon molecules, designated C2, fluorescing when exposed to ultraviolet radiation emanating from our sun. Upon absorbing this high-energy solar radiation, these C2 molecules subsequently re-emit the energy at precisely defined wavelengths. Human visual perception interprets this re-emitted light as the distinct color green. This well-documented emission signature is scientifically termed the swan bands, a series of specific emission lines readily observable during spectroscopic analysis. These spectral markers are a definitive indicator of diatomic carbon presence. However, observations from the celestial body designated 3I Atlas reveal a significant anomaly. C2 molecules are absent in any detectable concentration. Spectroscopic data returned from the location known as Canary 4 shows no evidence of the characteristic swan bands. Crucially, there are no discernible peaks at the distinctive wavelengths of 516 nanometers or 563 nanometers, where such emission lines would inevitably appear if C2 were present and responsible. Consequently, the diatomic carbon species presumed to generate the green glow is demonstrably missing from these observations. Furthermore, cyanogen, another compound occasionally capable of producing similar greenish emissions, is also entirely absent. All the conventional gases typically associated with this specific chromatic output fail to appear in the spectra. Therefore, the fundamental chemistry expected to produce this particular green coloration is notably absent. This critical absence presents a profound enigma. If the established chemical source is missing, then the origin of the observed green light remains a significant scientific puzzle. This conundrum has become a persistent source of conjecture for spectroscopists in recent weeks. The phenomenon itself is unequivocally real. It constitutes no optical illusion nor an artifact resulting from image processing techniques. Multiple independent confirmations have been obtained using different telescopic systems, all attesting to the same observation. 3 Atlas consistently exhibits a vivid, unmistakable green hue. Yet the mechanism producing this light appears to operate entirely outside the realm of the traditional, well-understood processes. One plausible, though speculative explanation under consideration involves charged dust grains fluorescing. When microscopic dust particles within the atmosphere become subjected to intense ultraviolet radiation, they possess the physical capacity to emit light.
It ceases to be viewed merely as a conventional common nucleus or simply as an inert rocky body. Instead, it emerges as something markedly more exotic, an ultra-low density aggregation of dust particles, held together with significant contribution from electrostatic forces alongside gravity itself. Within this structure, the distinction between a tangible solid and a diffuse cloud becomes profoundly blurred. Here, electrical charges are not static, but actively flow and continuously redistribute across the vast, interconnected fabric.
This dynamic environment suggests that electromagnetic interactions could potentially generate complex behaviors reminiscent of those observed only previously within laboratory-created plasma environments. This represents a profoundly radical concept. Crucially, this particular model stands out because it avoids immediate contradiction with a significant portion of the available observational data. Yet, if this radical hypothesis holds true, if 3I-ATLS indeed constitutes some form of charged dust conglomerate exhibiting collective behavior akin to a loosely bound plasma entity, then we are compelled to fundamentally reevaluate the very definition of a comet. This object demonstrably operates outside the established paradigms. It defies the conventional rules governing cometary spectroscopy, ignores expected thermal emission patterns, and exhibits activity levels and mechanisms that defy standard explanations. It appears to function under a distinct yet uncharted set of physical principles. Until these underlying principles are deciphered, each new observation seemingly adds another complex layer to the existing confusion rather than clarifying it. Furthermore, the very act of investigating this enigmatic object using such a diverse array of observational wavelengths only intensifies the sense of profound confusion. As increasingly different teams utilize these varied spectral windows to probe 3I-ATLS, the overall picture they construct becomes not more unified, but increasingly fragmented and contradictory. This situation, characterized by conflicting interpretations derived from the same celestial target observed across the electromagnetic spectrum, represents what might be termed a silent data war. Science ideally strives for convergence, for disparate lines of evidence to coalesce towards a shared understanding of truth. Regrettably, the current evidence regarding 3I-ATLS presents a landscape where different wavelengths reveal seemingly incompatible realities, making the pursuit of a coherent narrative exceptionally challenging. The collective picture becomes increasingly defined with each additional dataset. This established process, however, completely breaks down with the comet designated 3-Atlas. Instead of converging on a shared understanding, the situation grows more perplexing with every new team that observes it. The conflict between datasets intensifies rather than diminishes. Visible light observations of 3-Atlas, conducted by numerous independent groups, present a remarkably consistent and unambiguous picture. The data consistently reveals a complete absence of any significant gaseous emissions. Detailed spectral analyses confirm this view, showing spectra that are notably clean and featureless, dominated solely by dust signatures. Each subsequent team scrutinizing the visible light data arrives at the identical conclusion: no emission lines, no absorption features indicative of active chemical processes, nothing suggesting substantial cometary activity. Based solely on the visible light evidence, 3-Atlas appears to be a lifeless body exhibiting only sporadic dust ejections, potentially triggered by solar radiation pressure or structural instability. The case, it seemed, was effectively closed. This apparent certainty, however, encountered a profound complication when radio astronomers began submitting their observations. Some radio teams, though not universally, reported intriguing and unexpected signals. These weren't powerful emissions demanding immediate attention, but rather subtle hints of the hydroxyl radical, a well-known chemical breakdown product of water molecules. While the signals detected were weak, far from constituting a definitive, headline-making discovery, they were sufficiently distinct to cause significant scientific pause. The presence of even trace hydroxyl points towards water, and water implies the existence of volatiles. This shattered the initial assumption that 3-Atlas was merely a dust-laden rock. It suggested a more complex, potentially active nature. The contradiction deepened dramatically when other radio research teams, utilizing comparable wavelengths and similar instrumentation, detected absolutely no such signals. Some groups reported only a very faint oxygen line, while others saw nothing at all. This persistent and maddening inconsistency across radio observations defied explanation, leaving the true nature of 3 Atlas stubbornly opaque. It's critical not to jump to the conclusion that an error has occurred simply because observations appear contradictory. These findings come from highly trained astronomers, professionals who conduct their work as a vocation. They utilize sophisticated, precisely calibrated instruments and possess extensive expertise in meticulously accounting for various complicating factors inherent in astronomical observation. This includes effectively managing potential sources of noise, interference, and the distorting effects of Earth's atmosphere.
Therefore, if these experts are obtaining different results, it is far from a simple matter of human oversight, such as failing to complete a calculation step correctly. A plausible explanation for this discrepancy may involve artifacts arising from photo-dissociation processes. Here is how this phenomenon could operate. Even if the comet designated 3I/Atlas is not currently actively releasing water vapor into space at this moment, it is entirely possible that it experienced such activity days or even weeks earlier. The ejected water molecules would not vanish instantly. Instead, they would gradually disperse into the surrounding space. There, they would be relentlessly bombarded by sunlight, causing their molecular bonds to break apart. This solar radiation would fragment the water molecules into their constituent parts, hydroxyl radicals, OH, and individual hydrogen atoms. Consequently, when a radio telescope is directed towards 3I/Atlas, the signals it detects might not originate from fresh, ongoing emissions directly from the comet's nucleus. Instead, the instrument could be picking up the lingering signature of those dissociation products, specifically the oxygen atoms liberated from the water molecules long ago. This situation is analogous to detecting the lingering scent of smoke hours after a fire has been completely extinguished. The smoke itself is undeniably present and real, yet the source fire is no longer burning. This scenario could readily explain why the detections of oxygen become so faint and why they vary significantly from one observation to the next. The presence and detectability of these dissociation fragments depend entirely on complex spatial and temporal factors. The specific location of these hydroxyl radicals and hydrogen atoms at the precise moment of observation determines whether they are caught within the telescope's beam or have drifted beyond its reach. However, this intriguing explanation itself encounters significant challenges. If 3I/Atlas had indeed been producing substantial amounts of water vapor relatively recently, the scientific expectation would be to observe other accompanying phenomena. Specifically, one would anticipate the detection of signals associated with hydrogen emission. Furthermore, the process of water sublimation is typically linked to an increase in dust production from the comet. The absence of any discernible hydrogen emission signatures or any measurable change in the dust emission rate associated with this comet poses a substantial puzzle that this dissociation artifact theory must address. The OH signals, should they truly exist, appear as isolated phenomena detached from any broader pattern of volatile activity. This peculiar isolation raises immediate questions. Compounding the mystery is the fundamental challenge of calibration. Different research teams utilize distinct comparison stars to calibrate their precise instruments.
Furthermore, observations occur at varying times of day, from different geographical locations, and under fluctuating atmospheric conditions. For the vast majority of celestial objects, these variations are negligible, yielding consistent results. However, the object designated 3I Atlas exhibits a startling sensitivity to everything. The mere time of observation proves significant. The state of the solar wind impacts readings. Even the precise angle from which it is observed might alter the outcome. It's as if the object itself is in constant flux, shifting between different states or configurations. Whether one captures it in one particular state or another hinges upon factors beyond complete human control. This scenario exemplifies what astronomers term the snapshot science problem. One directs a telescope at an object, collects a single measurement, and effectively captures just one frame from a dynamic movie one is not actively watching. If the object remains stable, this single frame suffices, revealing all necessary information. But if the object is inherently changing, cycling through different behaviors on timescales shorter than typical observation windows, then each research team, operating under their unique circumstances, inevitably records a different moment within that complex cycle. All the collected data points are accurate, but each represents only a fragment of the whole picture, an incomplete snapshot. This leads directly to the central and unresolved debate. Is 3I Atlas a single, consistent object whose appearance shifts depending solely on the moment of observation? Or is it fundamentally a multi-state system? Does it genuinely cycle between distinct physical configurations? Determining the answer hinges upon reconciling observations that, while individually correct, tell only partial stories due to the inherent limitations of capturing only fleeting glimpses. What governs these state changes? What precisely dictates whether the comet resides in a dormant, dusty phase, a state of emitting specific spectral signatures, or perhaps enters a phase where it launches powerful jets? It is precisely at this juncture that the phenomenon acquires a profoundly puzzling character. The concept of observer-dependent behavior, where the very act of observation influences the system being observed, is not an unfamiliar one within the realm of quantum mechanics. There, the mere process of measurement is known to fundamentally alter the state of the entity under scrutiny. However, applying such principles to celestial bodies like comets presents a stark contrast. Comets, by their very nature, are considered large, classical objects whose behavior adheres to well-understood, predictable laws of physics. They exist independently, seemingly indifferent to whether they are observed or not. Yet the case of Comet 3I Atlas appears to transgress this fundamental assumption.
Its behavior demonstrably hinges upon external conditions that fluctuate dramatically from one moment of observation to the next. Factors such as the intensity of the solar wind buffeting its surface, the orientation of surrounding magnetic fields, and potentially even properties inherent to the local interplanetary medium all seem to play a decisive role. The object itself is not merely passive, it actively engages with its ever-changing environment in ways that directly shape the phenomena we witness. The foundational principle governing comet spectroscopy has traditionally been unwavering. Jet intensity correlates directly with gas emission. Bright, prominent jets signify significant outgassing activity, a substantial release of volatile material. Conversely, faint or weak jets indicate considerably less outgassing. The complete absence of jets logically implies a total lack of gas emission. This cause and effect relationship was considered as reliable and consistent as any other principle within astronomical observation. However, Comet 3I Atlas utterly shatters this established rule. Observations reveal peak jet activity occurring in complete absence of any detectable gas signature. It is akin to witnessing the impossible, water flowing uphill against the natural order. The conventional physics governing such interactions dictates that this outcome should be unattainable. Yet paradoxically, it manifests regardless of theoretical expectations. Consequently,
Some astronomers are now proposing that Comet 3I Atlas might exist in a unique state they term a metastable dust plasma. This sophisticated description suggests the object occupies a delicate equilibrium, balanced precariously on the boundary between distinct physical states, between solid material and gaseous matter, between neutral particles and charged entities, and between stability and inherent chaos. Minor fluctuations possess the remarkable capacity to instigate a transition between distinct states within certain enigmatic celestial bodies. Such subtle influences can precipitate profound alterations in observable behavior, all without necessitating the conventional processes involving volatile substance sublimation. This concept remains genuinely exotic, the sort of phenomenon that appears to unfold solely under highly specific and exceptionally rare cosmic conditions. Yet, if one entertains the possibility of invoking such rarities, it is crucial to acknowledge that the object designated 3I/Oumuamua already represents an interstellar traveler, an occurrence of extreme improbability bordering on uniqueness. The ongoing scientific inquiry continues to accumulate data. Subsequent observations present a complex picture. Some analyses support a composition consisting solely of dust and rock, while others suggest the potential presence of vanishingly small quantities of gaseous material.
The object's characteristic jets manifest and then disappear with unpredictable timing. A distinctive greenish luminescence flickers erratically. Amidst this observational flux, astronomers are gradually comprehending a profound implication. 3I Oumuamua resists categorization within any established framework for solar system bodies. It appears to be something entirely novel, demanding the creation of an entirely new conceptual container to accommodate its unique properties. And the necessity to build such a conceptual container naturally prompts further inquiry. What other entities might share these characteristics and belong within this burgeoning new category? The possibility arises that if 3I Oumuamua constitutes one instance, there could exist other similar objects traversing the vastness of interstellar space. This prospect simultaneously raises significant and somewhat unsettling questions concerning the current understanding of the universe's fundamental composition and processes. This segment, titled The Identity Crisis of Interstellar Visitors, examines a pivotal moment in astronomical discovery. Astronomers have now confirmed the passage of 3 distinct interstellar objects through our solar system within recent years. These are entities that originated outside our stellar neighborhood, having journeyed across the immense gulfs separating stars to briefly traverse our cosmic vicinity before disappearing back into the profound darkness of space. Each was anticipated to impart valuable insights, to teach scientists about the conditions prevalent in planetary systems orbiting other stars, to reveal what forms of debris such systems generate, and to illuminate the nature of the diffuse material fields that permeate the galaxy. The unexpected arrival of interstellar visitors meant to illuminate the unknown often had the opposite effect, casting deeper shadows of confusion. The very first of these intruders, designated Oumuamua, materialized suddenly in the 10th month of 2017. Its motion was so swift and its trajectory so distinctly hyperbolic, defying the sun's gravitational embrace, that astronomers instantly recognized its extraterrestrial origin. A frantic race began, scrambling powerful telescopes to capture any data before the object vanished beyond the solar system's reach. What they observed defied easy explanation. As Oumuamua journeyed away from our sun, it inexplicably gained speed,
exhibiting a distinct non-gravitational acceleration. This subtle thrust suggested a mechanism like outgassing, a common behavior for comets. Yet, despite intense scrutiny, no vapor was detected. Crucially, there was no surrounding coma, no sweeping tail, and spectroscopic analysis revealed no telltale signatures of volatile ices or gases.
Instead, the object appeared as an extremely elongated, tumbling body, reflecting sunlight much like bare rock, while simultaneously behaving as if propelled by an unseen engine. Numerous theories emerged to explain this enigma: exotic ice compositions, speculative light sail concepts, or even natural hydrogen outgassing, but none provided a complete and satisfying fit. Oumuamua remained undeniably strange, yet its weirdness followed a consistent, if perplexing, pattern. Then, in the year 2019, Comet Boris arrived. Astronomers, weary after the puzzle of Oumuamua, found themselves drawing a collective, profound breath of relief. Finally, an interstellar visitor seemed to conform to established rules. Boris presented itself unmistakably as a comet. It looked like one, it acted like one, and its spectral fingerprint confirmed its cometary nature. Gas emissions were clearly present alongside significant dust. It possessed the classic appearance of a coma surrounding its nucleus and displayed the familiar sweeping tail. Boris moved according to expected celestial mechanics, behaving like any comet discovered within our own solar system. While subtle differences existed, its composition was notably enriched in carbon monoxide. These variations felt comprehensible, natural extensions of known processes. This comet appeared precisely as scientists anticipated an interstellar traveler should look and behave. Boris, for a moment, restored faith that the universe operated on reasonably predictable principles. This sense of reassurance, however, proved fleeting. The subsequent arrival of another interstellar object, Comet Atlas, shattered the fragile order Boris had brought. Atlas presented a fundamental challenge. It did not align with the characteristics of Oumuamua, and it failed to match the expected profile of Boris either. Its behavior defied easy categorization, plunging astronomers back into a state of bewildered uncertainty and reopening the very questions Oumuamua had posed, now compounded by Boris's apparent normalcy. This extraordinary object occupies a perplexing position within the cosmos, residing in a conceptual category that lacks a formal designation. It exhibits dynamic behavior, reminiscent of the comet Borisov, yet crucially lacks the telltale gaseous signature characteristic of such bodies. Simultaneously, it possesses the profound spectroscopic emptiness observed in the interstellar object Oumuamua, yet it is demonstrably active rather than consistently inert. The effect is profoundly disconcerting, almost as if an observer had meticulously selected the most enigmatic characteristics from each of these two well-known visitors and deliberately fused them into a singular entity. This synthesis appears intentionally engineered to challenge the very foundations of astronomical understanding and provoke intense intellectual frustration among scientists.
So, what definitive identification can be assigned to this baffling entity? Speculation abounds, with theories ranging wildly. The first prominent hypothesis proposes it could represent a primordial planetesimal, essentially a surviving fragment originating from the turbulent infancy of another planetary system. Imagine a remnant from the chaotic epoch of planetary formation surrounding a distant star, composed of material that coalesced billions of years ago but never fully consolidated into a larger body. Such an object would be ancient, possessing a composition fundamentally alien to anything encountered within our own solar system. It would consist of fragile, primordial aggregates of dust compressed over immense timescales, but remaining inherently unstable. Should such a relic venture into the inner regions of our solar system, the increased solar radiation would likely induce fracturing and the shedding of dust particles. Crucially, this process would not generate the familiar cometary coma or tail of volatile gases, as this object never contains significant volatiles to begin with. It embodies the leftover building blocks, the primordial residue, from planet formation occurring elsewhere in the galaxy. The second hypothesis ventures into even more exotic territory, suggesting the object might be a fragment originating from a supernova explosion. This scenario involves the cataclysmic death throes of massive stars. When these colossal entities detonate, they release staggering quantities of carbon-rich dust into the interstellar medium. Over time, some of this dispersed material could coalesce under gravity to form larger, denser conglomerates. Unlike the ancient planetesimal, this proposed origin would make the object remarkably young, potentially formed within the relatively recent cosmic timeframe of a few million years. Its composition would be dominated by complex carbon compounds and materials entirely absent from the familiar catalog of solar system objects like asteroids or comets, presenting a completely unique chemical signature. And due to their formation occurring under extreme and violent conditions, the internal architecture of these celestial bodies could fundamentally differ from our established understanding of cometary interiors. Their response to solar proximity, manifesting as observed jets, might not involve sublimation processes at all. Instead, the jets could represent dramatic structural failures, triggered as the object's unique composition reacts to intense solar heating in ways entirely alien to the behavior of typical comets. This leads to the third hypothesis, the exotic plasma body theory. This concept proposes that Object 3 Atlas may constitute a partially ionized dust cloud, its cohesion primarily governed by electromagnetic forces rather than gravitational pull. It exists in a state neither fully solid nor purely gaseous, occupying a distinct intermediate phase.
Furthermore, the concept of the object being a vast plasma body struggles to reconcile its presence with high-resolution imagery that clearly depicts a seemingly solid structure, contradicting the expected diffuse nature of such a formation. Finally, the hypothesis involving an engineered construct, potentially by an alien intelligence, encounters a significant hurdle: the conspicuous absence of any detectable heat signature, radio emissions, or other obvious indicators of active technological mechanisms powering such an entity. Each proposed model, while successfully addressing some aspects of the puzzle, simultaneously generates new inconsistencies or fails to resolve key mysteries. Astronomers grappling with this situation often describe a feeling akin to being trapped within a multiple-choice examination where every available answer option possesses both elements of correctness and significant flaws. This pervasive sense of dissatisfaction, the persistent impression that none of the currently available explanations fully cohere with the totality of the observations, is fostering a growing consensus within the astronomical community. This consensus suggests that 3I Atlas might represent something genuinely unprecedented, something fundamentally new. It may not simply be a minor variant of known astronomical objects like asteroids, comets, or planets, but rather an entirely novel category of cosmic phenomenon. This would necessitate the development of entirely new terminology, entirely new theoretical frameworks, and entirely new models to describe and understand it. The philosophical implications of such a discovery are immense and difficult to overstate. For centuries, humanity's endeavor has been the systematic cataloging and classification of the universe's contents, meticulously placing celestial bodies into neatly defined categories:
Planets resided within one designated region, asteroids in another, comets in specific classifications, and rare interstellar visitors occupying their own distinct group. However, the inherent nature of the cosmos operates entirely independently of these human-imposed structures and classifications. Nature itself generates objects and phenomena according to its own internal logic and processes, unconcerned with the neat boxes we strive to contain it within. The emergence of 3I Atlas seems to impart a profound lesson. Our existing cosmic classification systems possess inherent limitations. It suggests the existence of entities, potentially numerous, that defy categorization within established frameworks. Consequently, we find ourselves confronting a celestial visitor that categorically refuses identification. This enigmatic object presents a dichotomy. On one hand, it could represent a phenomenon exhibiting remarkably natural properties governed by physical laws we have yet to fully comprehend or model.
Alternatively, it might embody something profoundly artificial, an occurrence that contradicts all our current scientific understanding. There is no plausible intermediary explanation. Furthermore, as additional observational data accumulates and our understanding deepens, the fundamental contradiction does not dissipate. Instead, it intensifies, becoming more pronounced. 3I Atlas thus forces a critical choice. It either reveals that the universe operates with a strangeness beyond our wildest expectations, or it provides compelling evidence that we are not the sole intelligent inhabitants. Regardless of the outcome, the subsequent developments will irrevocably transform the field of astronomy. Resolving this paradox necessitates abandoning conventional caution and seriously contemplating possibilities we typically exclude from consideration. This leads us to Part 6, the Duster's Propellant Framework. The central question becomes, can charged dust grains generate effects mimicking thrust? Let us now direct our attention to the nature of cosmic dust. This is not the mundane residue found gathering on household surfaces. Instead, it refers to the pervasive microscopic particles that permeate space itself. These grains vastly outnumber the stars within our galaxy. While each individual particle is infinitesimally small, requiring microscopic magnification for visibility, their collective mass is significant enough to obscure vast regions where new stars are born. This dust, however, is far from inert. It does not merely drift aimlessly. It actively engages with electromagnetic radiation, interacts dynamically with magnetic fields, and under specific, precisely defined conditions can attain considerable velocities. It is a fact that most individuals often overlook. Dust can acquire a charge. When sunlight strikes a dust particle floating in the vacuum of space, the photoelectric effect may cause electrons to be dislodged from its surface. As a result, the once neutral particle now carries a positive charge. This newly charged particle becomes influenced by electric fields. The solar wind, which is a continuous flow of charged particles emanating from the sun, is accompanied by its own magnetic field. When charged dust encounters this magnetic field, forces are exerted upon it. Magnetic pressure coupled with electric repulsion causes the dust grain to accelerate. Although the initial acceleration is minimal and gradual, these subtle forces accumulate over time. In the vicinity of a comet, a complex electrical environment can develop. The comet's nucleus has the potential to accumulate charge as solar radiation bombards it. The surrounding dust cloud becomes a mixture of charged and neutral particles, where plasma physics becomes significant. In the realm of plasma physics, peculiar phenomena occur. Particles can arrange themselves into unexpected configurations. Instabilities can arise and dissipate.
Under specific conditions, coherent structures may emerge, forming regions where charged dust moves collectively in a manner that appears almost purposeful.
Could this phenomenon possibly account for the jets observed in Atlas? Could electrostatic acceleration possess sufficient energy to generate the symmetrical plumes that have long puzzled scientists? The principles of physics suggest that it is indeed possible. Laboratory experiments have demonstrated that when dust particles are charged and positioned within an electric field, they follow the field lines in a predictable manner. Imagine a scenario where a comet, designated 3 Atlas, manages to maintain a remarkably strong separation of electrical charge across its surface. One distinct region holds a positive charge, while another, nearby area, possesses a significant negative charge. Under such conditions, the fundamental principles of electromagnetism could theoretically propel dust particles away from the comet's surface. This expulsion wouldn't rely on the familiar push of escaping gases generated by sublimation. Instead, the raw power of pure electromagnetic attraction and repulsion could be the driving force. However, achieving such clean directional ejection faces a profound challenge. Nature itself is inherently messy and disordered. When a vast collection of dust particles becomes electrically charged, they rarely do so in a perfectly uniform manner. Individual grains vary significantly in size. Some are larger, others smaller. Their material properties differ drastically. Some grains conduct electricity relatively easily, while others act as effective insulators. Furthermore, the environment is far from uniform. Some particles might reside in deep shadow, shielded from direct solar radiation, while others bask in intense, unfiltered sunlight. The result within this complex cloud is almost invariably a chaotic and unpredictable mixture. Once these differently charged particles begin to move under the influence of electromagnetic fields, they do not follow neat, organized streams. Instead, their trajectories become wildly scattered. They collide violently with one another, bouncing off in unpredictable directions. These interactions foster the formation of constantly shifting, irregular structures that change shape and configuration from moment to moment. True symmetry and reliable, repeatable patterns are the exception rather than the rule in such uncontrolled settings. Despite this inherent chaos, observations of Comet 3 Atlas reveal something remarkably different. The jets of dust emanating from this comet appear astonishingly clean and precisely balanced. If purely electrostatic forces were responsible for driving these jets, some unknown mechanism must be actively constraining, channeling, and focusing these electromagnetic interactions.
This mechanism would need to impose order on the electrical distribution in ways that natural processes, with their unpredictable variations, rarely achieve. Consider the analogy of attempting to create 3 perfectly spaced fountains using only water pressure sourced from a multitude of random underground springs. The underlying physics of fluid dynamics theoretically allows for such an outcome. Yet, the sheer improbability of this occurring naturally without any guiding structure borders on the astronomically improbable. Crucially, the Rosetta spacecraft provided us with compelling evidence suggesting that this kind of surprisingly organized behavior might indeed be possible within the complex environment surrounding a comet nucleus. During its extended mission orbiting Comet 67P Churyumov-Gerasimenko, Rosetta recorded numerous events where dust particles exhibited movement in coherent, organized streams. These streams appeared structured in ways that could not be explained by the effects of gas drag alone, hinting at the potential influence of forces, perhaps electromagnetic in nature, that could impose such order amidst the expected chaos. Previous research proposed that electrostatic forces might explain the observed dust behavior on comets. This theory suggested dust grains could acquire an electrical charge, subsequently responding dynamically to localized electric fields present in the comet's vicinity. However, the resulting dust structures predicted or observed under such conditions tended to be relatively small, short-lived, and morphologically inconsistent. These characteristics stood in stark contrast to the striking, sustained, and symmetrically organized plumes currently being detected emanating from 3 Eisen Atlas. The observed fluctuations in brightness provide another significant clue to unraveling this phenomenon.
When Three Eyes in Atlas exhibits variations in its luminosity, dimming or brightening over time, this change does not necessarily signify an increase or decrease in the total volume of dust being ejected. Instead, a compelling alternative explanation involves the redistribution of electrical charge among the dust particles already present within the coma. Imagine a dense cloud of particles where suddenly a substantial portion becomes significantly more highly charged. This alteration in charge state would fundamentally change how these particles interact with light. Highly charged particles would reflect sunlight in distinct patterns and scatter it across different angular distributions compared to their less charged or neutral counterparts. As a result, the net brightness perceived from the entire coma could shift noticeably even if the overall quantity of dust material remained unchanged. This potential mechanism for brightness variation through internal charge redistribution is plausible on relatively short timescales.
Such rapid changes, occurring over periods measured in hours, could be triggered by external factors like fluctuations in the solar wind's intensity and composition, or by intrinsic changes in the comet's orientation relative to the Sun. Computer simulations modeling the behavior of charged dust streams reveal intriguing patterns. Under typical conditions, the system often descends into apparent disorder, characterized by disordered particle movements and chaotic distributions. Nevertheless, the simulations demonstrate that introducing specific boundary conditions can alter this outcome. If the model assumes that dust is being released from particular, well-defined locations on the comet's surface, and crucially, that these release points consistently maintain distinct electrical properties, it is possible to generate more organized, coherent streams of charged dust. Achieving this order, however, is not straightforward or guaranteed. It requires precise maintenance of these critical boundary conditions. The key lies in stabilizing the charge sources themselves, the specific surface points releasing dust with consistent electrical characteristics, even as surrounding environmental factors fluctuate dynamically. This intricate balancing act points toward the feasibility of the electrostatic fountain model as a potential mechanism explaining the observed plumes. Imagine the core of 3I Atlas not as an unchanging orb of material, but as an intricate entity divided into varying electrically active areas. Perhaps through a blend of varying composition, temperature differences, and exposure to radiation, some areas become intensely charged, whereas others stay neutral. Dust particles resting on these charged regions would encounter repulsive forces. As the charge accumulates, the repulsive force grows. Eventually, it surpasses the weak gravity that holds the particle in place, and the grain ascends, not with a violent thrust or an explosion, but with a gentle upward acceleration. More particles join in, resulting in a continuous flow. Now here's the captivating part. If there are several charged regions positioned symmetrically around the object, you would witness multiple streams lifting off at the same time, each following comparable paths as they all react to similar forces. The symmetry of these jets would mirror the arrangement of the charge distribution. And if something periodically neutralizes those charges, possibly due to an influx of electrons from the solar wind or a change in the object's magnetic surroundings, the fountains would cease. Afterward, the charge would accumulate again and they would restart. It's both sophisticated and physically viable. It doesn't necessitate the presence of volatile substances or heat, which are typical in cometary mechanisms, but it does require 3I Atlas to possess an internal structure capable of sustaining distinct electrical zones.
The object in question must possess more than merely a loose accumulation of dust. It requires a distinct, organized structure. This structure needs defined boundaries and interfaces capable of sustaining the separation of electrical charges. Essentially, it necessitates three distinct atlas-like bodies, functioning collectively as a vast capacitor. Their purpose would be to store significant electrical energy and then release it in controlled bursts. Could such a natural phenomenon occur?
possibly under exceptionally rare circumstances. This would demand very specific materials interacting over immense durations within the frigid depths of interstellar space, potentially yielding structures capable of this function. However, here lies an undeniable fact. Astronomers have never observed such a configuration before. Not within any comet, not within any asteroid, and not within any small body examined throughout our solar system. This absence of precedent forces astronomers to consider two possibilities. Is this 3 Atlas the very first instance of its kind successfully observed? An extraordinary stroke of fortune, capturing something exceptionally rare yet naturally occurring? Or is it something entirely different? Something that does not arise spontaneously through the familiar processes of accretion and collision, but instead through mechanisms requiring much deeper contemplation. Furthermore, the striking symmetry observed in its jets presents a persistent puzzle for scientists. Symmetry in natural phenomena often serves as a crucial clue, revealing underlying formation processes or inherent structural principles. Part 7 delves into reconstructing the jet geometry, focusing on why this symmetry constitutes a significant anomaly. When researchers stacked multiple images of 3 Atlas, captured over several hours, a remarkable pattern emerged. The jets do not vanish and reappear randomly. Instead, they maintained fixed positions relative to the nucleus. Each distinct plume consistently originates from roughly the same specific location on the celestial body's surface. These plumes extend in unchanging directions, retain their characteristic shapes over hours, and, when active, sustain this stability over days. This persistent geometric regularity demands explanation. This remarkable consistency in observation forms the cornerstone for scientists to meticulously reconstruct the three-dimensional structure of activity occurring around the celestial body under study. The underlying methodology itself is not a recent development. Astronomers have successfully employed multi-perspective techniques for decades to chart the dynamic jets emanating from cometary nuclei. By capturing sequential images from various vantage points as Earth traverses its orbital path, and then integrating these visual records with the precise knowledge of the comet's rotational behavior, researchers can meticulously deduce the specific surface locations where each jet originates. When examining ordinary comets, the resulting complexity is immediately apparent. Jets emerge seemingly chaotically from diverse geological features, erupting from crater interiors, spewing forth from sheer cliff faces, or issuing from rugged, irregular terrain. One might observe 5 distinct jets originating from a single northern hemisphere region, juxtaposed with 3 emerging from the southern counterpart, each jet directing its material in entirely different orientations dictated solely by the local landscape's peculiarities. This constellation of activity represents pure geological chaos translated into streams of gas and particulate matter. In stark contrast, the observations of Atlas reveal a profoundly different pattern. Instead of numerous jets, Atlas typically presents 2 or occasionally 3 remarkably well-aligned, fan-shaped structures. These are not manifestations of random geological vents, but rather appear to originate from specific points exhibiting an almost mathematical precision in their arrangement. Upon mapping these emission structures back to the comet's core, while carefully accounting for the complex interplay of the nucleus's rotation and our changing viewing perspective, the resulting configuration bears far less resemblance to the messy outcomes of natural geology and much more evocative of deliberate design. The emission points on Atlas are discerned to be spaced with even intervals encircling the equatorial region, or arranged in a distinct triangular formation, or even positioned precisely at diametrically opposed poles. Determining the exact geometric configuration remains a subject of active discussion within the scientific community, primarily due to the current limitations imposed by the available high-resolution observational data. Nevertheless, one conclusion stands firm: the patterns observed
are categorically non-random. Natural comets, shaped by a violent and unpredictable history of collisions, extreme temperature fluctuations, and the development of fissures and fractures following inherently chaotic paths, simply do not produce such orderly arrangements. The formation of jets on certain celestial bodies appears intrinsically linked to inherent structural vulnerabilities. Imagine fissures or fault lines traversing the object's crust. If such a weakness exists, jet activity may manifest in close proximity nearby. However, this process lacks geometric precision. The jets do not exhibit perfectly spaced arrangements. Symmetry, a hallmark of orderly natural systems, is conspicuously absent. This irregularity extends to the object's rotational behavior.
For the jet's positions to remain consistently anchored relative to the central nucleus as the body spins, they must originate from fixed points on the surface itself. Consequently, astronomers anticipate detecting a distinct rotational period, a rhythmic cycle where different facial features of the object become visible to observers. During this predictable sequence, specific jets should appear and disappear as their source locations turn towards or away from the viewer. This expectation aligns with standard methodologies used to analyze cometary activity. Yet when scientists applied this technique to investigate the rotational period of the object designated 3 Atlas, their efforts encountered a significant obstacle. The cycles of activity failed to correspond with any consistent rotational pattern. On occasion, jets activated precisely when their predicted spin orientation suggested they should be dormant. Conversely, jets remained silent when the calculated rotation indicated they ought to be vigorously active. This phenomenon is termed rotational discordance, essentially describing an object that defies established physical norms. One potential explanation involves complex rotation. Perhaps 3 Atlas does not execute a stable single-axis spin like a top. Instead, it might tumble chaotically, precessing around multiple axes simultaneously. This tumbling motion, common among certain asteroids, particularly those with elongated shapes or composed of loosely bound rubble, would inherently create irregular viewing patterns. While complex rotation is intricate, it remains fundamentally predictable once its rotational vectors are mapped. The sequence of events would repeat. However, observations of 3 Atlas suggest the sequence either alters unpredictably or exhibits no discernible repetition at all. This defiance of predictable tumbling patterns has prompted some researchers to pursue an alternative hypothesis – magnetically gated emission. Here lies the proposition. Imagine a scenario where the jets of a celestial object are not governed by its rotation or the intensity of sunlight, but by intricate magnetic fields. Specifically, these jets are influenced by the interaction between any internal magnetic field the object might possess and the external field carried by the solar wind. When these fields align in certain ways, specifically when the magnetic tension reaches a certain threshold, material is released. Conversely, when they do not align, no activity occurs. The jets would still emanate from fixed points on the surface, but those points would only be active when the magnetic conditions are favorable. This would explain why the activity does not correlate with rotation, as the magnetic trigger operates independently of the object's spin, focusing solely on the magnetic environment.
A sudden shift in the intensity of the solar wind or a change in the direction of the interplanetary magnetic field could activate the jets, regardless of which part of the nucleus faces the Sun. This would make 3 Atlas responsive to its electromagnetic environment in ways that most comets are not. However, there is a significant caveat. For this mechanism to work, 3 Atlas would need to be magnetized, not weakly magnetized like most rocks, which retain traces of ancient magnetic fields frozen into their minerals, but actively magnetized, maintaining a coherent field strong enough to interact meaningfully with the solar wind. To date, we have never detected a comet with this property. Comets are composed of ice and dust, materials that do not generally retain strong magnetic fields. Some asteroids, particularly metallic ones rich in iron and nickel, can be magnetic, but such conditions are rare among comets. The characteristics under discussion fundamentally distinguish these objects from one another, rooted in entirely separate evolutionary processes. Should Atlas exhibit magnetic properties, this observation furnishes significant clues regarding its inherent composition or genesis. This could imply formation within a high-energy environment characterized by potent magnetic fields, such as proximity to a nascent stellar body or the chaotic aftermath of a stellar explosion. Alternatively, its material structure might incorporate metallic particles arranged throughout its form in a manner facilitating global magnetic behavior, effectively transforming it into a colossal bar magnet. Speculatively, and while this notion feels gravitationally heavy, the magnetic field might not originate from natural processes at all. Perhaps the field is actively engineered, sustained, or harnessed. The artificial hypothesis persistently resurfaces, not because proponents desire its validity, but because conventional naturalistic explanations increasingly demand implausibly intricate mechanisms. To account for the observed phenomena through purely natural means, one must posit interstellar objects possessing meticulously symmetrical internal architectures. Furthermore, these objects most demonstrably react to electromagnetic stimuli with exacting, recurring patterns. This constellation of requirements represents an exceptionally demanding suite of simultaneous conditions. While nature's capacity for improbable cosmic configurations is vast, there exists a threshold where attributing outcomes solely to random chance begins to feel scientifically unsatisfactory. The pronounced symmetry serves as the most compelling anomaly. It stands as an irreducible data point, persistently resisting dismissal. Each attempt to reconcile it within a naturalistic framework necessitates appending another layer of exceptional, finely tuned circumstances. The constituent dust must possess precisely calibrated charge distributions.
The internal architecture must exhibit flawless ordering. The ambient magnetic fields must align with minute precision. At this juncture, a critical question arises. Are we endeavoring to understand the phenomena we observe, or are we merely constructing elaborate narratives to deflect from them? Throughout the history of astronomy, there exists a compelling precedent for this particular mode of thought. Human ingenuity is repeatedly tested during moments when the scientific community, as a unified body, collectively determines that a specific celestial observation defies natural explanation, only to discover years later that their initial suspicion was profoundly accurate. This segment explores 5 distinct historical instances where astronomers, confronted with particularly anomalous data, concluded the observed object itself was fundamentally erroneous, only to learn the natural world had a more intricate explanation in store. The year 1996 marks the first such episode, centered upon the spectacular comet Hale-Bopp. This exceptionally luminous celestial visitor was astoundingly visible to the naked eye for an extended period, captivating observers with what many hailed as a true showpiece of the century, featuring a remarkable double tail. Radio astronomers meticulously pointed their sensitive instruments towards this rare cosmic performance, eager to analyze its composition by studying the gases it released. Instead of the expected natural emissions, however, their instruments captured baffling signals, distinct periodic pulses occurring at frequencies entirely unfamiliar to known molecular signatures in cometary science. For a brief and chaotic period, these perplexing readings ignited intense speculation within select scientific circles. Private discussions hinted at the most extraordinary possibility. Could this comet be harboring something artificial? Was a sophisticated probe potentially concealed within its vast dusty envelope? The tantalizing prospect of discovery spurred wild conjecture. Ultimately, the explanation proved far less sensational. Careful investigation revealed the signal stemmed from terrestrial interference. A nearby human-made satellite, positioned precisely within the telescope's sensitive field of view at critical moments, was the culprit.
Furthermore, complex reflections or emissions from advanced terrestrial radio sources generated patterns that, while unmistakably artificial, were entirely unrelated to the comet itself. Once the research team meticulously isolated these extraterrestrial sources of contamination and eliminated their influence from the data, the strange pulses vanished without a trace. Comet Hale-Bopp, despite its brilliance and the initial mystery, was confirmed to be nothing more than an exceptionally bright and beautiful comet, devoid of any hidden technological secrets. This episode, however, became a vital and enduring lesson within the astronomical community.
It underscored the critical importance of rigorous calibration, the constant vigilance required against terrestrial contamination, and the profound human tendency to perceive illusory patterns where none exist. Crucially, one aspect often overlooked in retellings of this story is this: the initial observations were genuine. The signals undeniably existed. The fundamental error lay not in detecting the anomaly, but in the subsequent interpretation of its origin. The core of the matter lay in interpretation. Should the contamination have gone unidentified, the true origin unrevealed, we would still be locked in debate over the pulse's significance. Fast forward to the year 2007. Comet Holmes, a relatively unknown periodic visitor to the inner solar system, captured global attention with an extraordinary event. Unlike the gradual brightening typical of comets as they near the Sun, Holmes detonated in luminosity. Overnight, its magnitude shifted dramatically from 17, rendering it invisible without substantial telescopic aid, to a striking 2.8. This placed it within easy reach of amateur astronomers and prepared observers using the naked eye. The resulting increase in brightness represented a factor of nearly 1 million times greater. It stands as the most colossal outburst ever documented within a comet. Astronomers immediately mobilized to observe the phenomenon, and the data they gathered proved profoundly puzzling. Crucially, the comet was not in the Sun's vicinity. Instead, it resided remarkably far out, well beyond the orbit of Mars, a region where cometary activity is typically dormant. No obvious catalyst emerged. There had been no impact event, no close celestial encounter, particularly with Jupiter, and no discernible alteration in its orbital path that could account for such a tremendous energy release. Various hypotheses rapidly emerged and proliferated. Perhaps a vast subsurface cavity had catastrophically collapsed, liberating tremendous quantities of trapped gases and dust simultaneously. Alternatively, it was conceivable that internal chemical reactions within the comet's nucleus had been progressing slowly, only to suddenly reach a critical threshold, triggering the explosion. Another compelling theory suggested the dramatic event might represent the catastrophic disintegration of a small celestial body. Years of subsequent study and analysis have yielded no single definitive explanation. Currently, the most widely accepted model proposes the delayed sublimation of exotic ices, unique frozen materials that possess the property of not vaporizing until they have been exposed to direct sunlight for prolonged periods, finally reaching a point of explosive transition. The dramatic outburst of Comet Holmes in 2007 certainly challenged expectations, yet it does not fully explain the sheer scale and astonishing speed of that particular event.
Holmes stands as a remarkable anomaly within the comet family, a vivid reminder that these icy wanderers can perform actions entirely unforeseen by science, even after centuries of dedicated observation and study. This sense of unpredictability is further underscored by the achievements surrounding Comet 67P Churyumov-Gerasimenko. In 2014, the European Space Agency spacecraft Rosetta accomplished a monumental feat. After traversing the solar system for 10 arduous years, Rosetta finally arrived at Comet 67P and became the first human-made object ever to achieve orbit around a comet nucleus.
Over the subsequent 2 years, this pioneering probe transmitted a treasure trove of unprecedented data back to Earth. The observations were so detailed that scientists could literally map individual boulders dotting the comet's rugged surface. Buried within this wealth of information, however, were moments that left Rosetta's scientific team deeply unsettled and perplexed. Phenomena like the so-called dust walls, for instance, events where the comet would suddenly expel vast sheets of dust, so incredibly dense they appeared as solid, impenetrable barriers. These structures, once ejected, moved outward in ways that defied conventional sublimation models, the standard explanations for how comet material evaporates. They were far too coherent and possessed an unnatural level of organization. For months, Rosetta scientists engaged in intense debate, wrestling with the origin and mechanism behind these unexpected formations. Only later did theoretical models begin to emerge that could partially replicate the observed behavior. These models suggested that a combination of electrostatic forces lifting dust particles and the drag exerted by escaping gases under very specific and previously unrecognized conditions might be capable of forming such sheet-like structures. Yet the very fact that this phenomenon surprised the entire scientific team, that such comet behaviors were not anticipated before Rosetta's arrival and detailed scrutiny, serves as a powerful testament to how fundamentally limited our understanding remains regarding the complex physics governing comets. Even for an object as closely studied as Comet 67P, which humanity literally orbited for 2 full years, new surprises continued to emerge unexpectedly. And then, of course, there is Oumuamua. Detected in 2017, this object became the first confirmed interstellar visitor to pass through our solar system. Astronomers observed a particularly perplexing characteristic as it departed, a measurable non-gravitational acceleration occurring as it left the Sun's influence. A subtle yet discernible increase in velocity was detected, necessitating a force exceeding what gravity and solar radiation pressure alone could typically generate.
The most straightforward hypothesis, outgassing, appears implausible given the complete absence of expected telltale signs. No emanating gas cloud, no diffuse coma surrounding the nucleus, and critically, no spectroscopic signatures indicating the presence of volatile materials were observed. What astronomers witnessed instead was a relatively simple, rocky body exhibiting a slight, persistent acceleration as it journeyed farther from the Sun. Proposed explanations for this peculiar behavior span from relatively conventional scientific theories to genuinely exotic possibilities. One plausible suggestion involves the release of hydrogen gas. Such emissions would be exceedingly difficult for most standard detection instruments to observe. Another intriguing, though highly speculative theory proposes the object might be a fragment of solid nitrogen, perhaps a debris chip originating from a distant Pluto-like world beyond our solar system. A third, more complex idea posits it could be a fragment of a shattered planet whose internal heat source remains active, gradually venting warmth in a matter capable of generating a minute thrust. Perhaps most controversially, one prominent scientific paper even advocated for the possibility of an artificial origin, suggesting it could be a light sail, a piece of technology explicitly designed to harness radiation pressure for propulsion, either functioning as intended or as a derelict relic. Naturally, this extraterrestrial technology explanation garnered significant public and media attention. However, the vast majority of professional astronomers remain skeptical, considering it the least likely explanation.
The crucial realization stemming from these investigations into objects like Oumuamua is not that any were definitively proven artificial. They almost certainly were not. The fundamental point lies in nature's remarkable capacity to produce phenomena that initially appear anomalous, behaviors that defy established expectations and leave observers questioning the very nature of what they're witnessing. In every instance, the scientific process initiates by rigorously pursuing natural explanations, often requiring the refinement and increased complexity of existing models until the observations find a coherent fit. The case of Oumuamua, however, presented something distinctively challenging. It was not merely a single, isolated anomaly that might be reconciled with explanations involving unusual forms of ice or internal cavities. Instead, it embodied multiple, layered contradictions persisting across diverse and independent types of astronomical observations, presenting a significantly more perplexing puzzle. The phenomenon defies conventional explanation. There exists no visible gas, yet powerful jets of energy erupt from its depths. A persistent green luminescence emanates from its structure, generated without any known chemical reaction.
Exquisite symmetry dominates its form, yet no discernible mechanism orchestrates its intricate design. Behaviors repeat with startling regularity, yet no clear initiating trigger governs its actions. Each fresh piece of observational data doesn't dissolve the enigma. Instead, it plunges the mystery deeper, layer upon layer. This constellation of unexplained characteristics compels serious consideration. Could we be witnessing an event akin to the original Holmes discovery? A phenomenon that is entirely natural, yet entirely unprecedented? Perhaps, given time and the development of the appropriate physical framework, its true nature will eventually reveal itself. However, a more unsettling possibility persists. Perhaps this object fundamentally resists explanation, defying comprehension regardless of how many complex adjustments we append to our existing cosmological theories. History relentlessly demonstrates the critical importance of anomalies. It is frequently the object that stubbornly refuses to conform to established paradigms that becomes the universe's most profound teacher. Whether the ninth-part object, Thrila, is instructing us about entirely new categories of natural phenomena or unveiling something conceptually different altogether, the underlying lesson is unequivocal. We should have internalized by now the fundamental truth that the universe possesses an endless capacity for genuine surprise. Still, understanding this principle intellectually remains a distinct challenge from embracing it on an emotional level. And currently, a significant cohort of astronomers finds itself grappling intensely with a possibility they dedicated their professional lives upholding as categorically impossible: the ninth-part object hypothesis. This is the rigorous scientific inquiry devoid of any science fiction embellishments. It is imperative to clarify one critical point. When scientists cautiously employ the term artificial to describe a potential explanation for Thrila, they are not conjuring images of mythical green extraterrestrial beings piloting a starship. They are not suggesting alien intelligences driven by purposes and intentions. Instead, they pose a far more constrained, technically precise question. Could the object's anomalous behavior be accounted for by presupposing it incorporates components that were deliberately engineered and assembled? This line of inquiry does not leap to conclusions about intelligence. It begins solely with the possibility of constructed elements. The fundamental challenge explored by SETI investigators revolves around the nature of potential extraterrestrial technological signatures. They consider scenarios where detecting objects might present significant difficulties: components that could currently be dormant,
deteriorated through time, or operating in manners entirely beyond our comprehension, yet existing nonetheless. This perspective shapes the entire search paradigm.
Crucially, the quest for intelligent life beyond Earth is not primarily conceived as an attempt to intercept alien dialogues or conversations. The central objective is far more subtle and scientifically measurable, identifying unmistakable technological signatures. These are the telltale indicators proving that an object within the cosmos was constructed deliberately by intelligent beings, distinct from formations arising solely through natural astrophysical processes. Engaging with this concept demands a rigorous scientific approach, one essential for distinguishing credible speculation from mere science fiction. Beginning with the underlying rationale, consider the hypothetical scenario involving the object designated 3 Atlas. If this entity were indeed some form of interstellar probe, even if rendered inert or technologically obsolete, or perhaps merely a surviving fragment originating from a much larger structure catastrophically destroyed eons ago, what functional purposes could plausibly explain its observed behaviors? One compelling possibility involves the realm of navigation and trajectory control. The deliberate, controlled release of material in measured bursts constitutes a perfectly legitimate method for adjusting a spacecraft's path. This maneuver is routinely performed by human-made probes utilizing thrusters. Therefore, if an interstellar craft required course correction without relying on conventional propulsion systems, the asymmetric expulsion of dust could effectively achieve this goal. The resulting jets would not necessitate immense power. Their success would depend solely on consistent, precisely directed output. Another highly plausible function involves deceleration or braking. An interstellar probe arriving at its destination solar system would inherently be traveling at tremendous velocities, far too high to permit detailed orbital investigation or study of the system's components. Slowing down becomes an absolute prerequisite. Utilizing chemical rockets for this purpose presents a profound logistical hurdle. They demand the carriage of vast quantities of fuel, a burden that renders them utterly impractical for journeys spanning interstellar distances. However, an alternative braking mechanism exists. If the probe possessed the capability to collect diffuse interstellar material encountered during its voyage, compress it efficiently, and then expel this compressed mass directly behind itself as it approached its target system, the resulting reaction force would impart a significant decelerating drag upon the craft. The persistent dust jets emanating from the mysterious object could well represent the lingering exhaust from a prolonged deceleration maneuver initiated many months ago, a process that may still be actively unfolding. This hypothesis gains further plausibility when considering the critical role of orientation control within the vacuum of space.
Absent any atmospheric resistance to dampen movement, objects naturally succumb to tumbling. Achieving and maintaining a precise alignment, such as keeping a specific surface perpetually aimed at a distant star or a nearby planet, demands the constant counteraction of any unwanted rotational forces. For such stabilization, a constellation of small, symmetrically positioned thruster jets encircling the object's equator would be the ideal solution. By executing precisely choreographed firings of these jets in sequence, it becomes possible to carefully accelerate or decelerate the spin, subtly adjust the object's rotational axis, and ultimately maintain the exact orientation required for its mission. Consequently, the observed lack of correlation between the 3 distinct dust jets and any detectable tumbling motion might not signify an unsolvable enigma at all. Instead, this apparent discrepancy could very well be the deliberate design principle in action. Turning to another possibility, communication stands as a more speculative avenue, yet one worthy of contemplation. What if the ejected dust particles are not a means of propulsion, but rather a sophisticated signaling system. Imagine material being expelled in meticulously planned patterns at precisely timed intervals, potentially forming detectable structures or patterns within the vast expanse of space. This concept might initially sound remarkably outlandish, bordering on the fantastical. However, upon reflection, one recalls that humanity has seriously entertained and even developed blueprints for astonishingly unconventional propulsion methods in the past. The historical Project Orion, for instance, contemplated harnessing the power of nuclear detonations for interplanetary travel. More contemporary proposals explore the use of colossal solar sails propelled by powerful lasers. Therefore, the notion of employing mass ejection as a purpose beyond simple thrust generation is not the realm of pure science fiction. It is firmly rooted in the domain of practical engineering solutions. Finally, a more straightforward explanation presents itself. The jets could simply represent a self-cleaning mechanism. Think of an object that has traversed the cold, dusty expanse of interstellar space. Over time, such a journey inevitably leads to the accumulation of extraterrestrial material upon its surface. This includes fine dust particles, frozen volatiles like ice, and impacts from countless microscopic meteoroids. The result is a gradual, persistent coating building up across the exterior. The periodic ejection of material could then represent the systematic shedding of these protective layers, material that the object has ceased to require for its ongoing journey or function. Should an underlying structure possess operational, observational, or functional capabilities, its sustained performance would inevitably necessitate the removal of accumulated material.
A scheduled release mechanism would achieve this objective. Expelling surface debris would reveal the original substrate, permitting renewed accumulation until the subsequent maintenance cycle commenced. Within this framework, a critical constraint emerges. If the 331 Atlas represents an artificial construct or incorporates artificial components, it must account for the conspicuous absence of specific signatures. Firstly, no excess thermal emissions are detected. An engineered object featuring active mechanisms would necessarily generate waste heat as a byproduct of operation. The failure to observe such thermal signatures implies either the object operates at ambient temperatures, is currently powered down, or utilizes energy conversion processes fundamentally devoid of significant thermal radiation output. While each scenario remains theoretically feasible, collectively they substantially limit potential explanations. Secondly, the complete absence of periodic radio emissions presents another significant challenge. Should functional electronic systems exist, or if communication protocols attempted to transmit signals, we would logically anticipate corresponding detections within the radio frequency spectrum. The consistent lack of such signals suggests either the absence of active transmitters, transmissions occurring outside our monitoring parameters, or emissions too feeble or sporadic to be captured by current technological sensitivity thresholds. Again, while not categorically impossible, this absence further narrows the field of plausible interpretations. Ironically, the featureless red spectral signature, initially perceived as a limitation, assumes the role of a compelling asset in this context. Consider the deliberate design strategy employed by an advanced civilization seeking to deploy an observational probe within a solar system. Their paramount objective would be stealth, avoiding immediate detection as an artificial entity while traversing the cosmic environment. Achieving this would necessitate meticulous camouflage. The ideal solution would involve enveloping the probe within ancient carbonaceous dust particles. This material precisely mimics the composition and spectral characteristics of natural cometary bodies. In such a state, the probe would effectively blend into the background celestial population, passing undetected as merely another insignificant dust cloud adrift among the stars.
Imagine an engineered core at the heart of the object. This central structure would be relatively small, exceptionally dense, and potentially inert.
Surrounding this core, whether through deliberate construction or the gradual accumulation of material over time, exists a substantial shroud composed of dust and ice. To an external observer analyzing its spectral signature, the entire object would appear entirely mundane. It would read as nothing more than a typical dirty snowball or a common carbonaceous aggregate, offering no hint of artificiality. However, within this deceptive exterior, hidden from direct detection, lies the potential for intricate engineering. Concealed compartments might house magnetic coils capable of generating complex fields. Reservoirs could store vast quantities of material primed for controlled venting. Fragments of what was once a fully operational system might also be present, now degraded beyond recognition, but retaining the latent capacity to produce organized phenomena under specific, unforeseen conditions. The elegance of this model lies in its power to reconcile the apparent contradictions within the observations. The thick outer shell of dust and ice directly accounts for the featureless spectroscopic signature. Simultaneously, the concealed interior mechanisms could potentially generate the observed jets through methods entirely independent of gaseous outflow. The symmetry of these jets may then reflect the engineered, systematic placement of venting points within the hidden core. Furthermore, the erratic on-off behavior observed could suggest the presence of residual control systems that still function sporadically, responding to internal protocols or external triggers currently beyond our understanding. Nevertheless, it is crucial to reiterate with absolute clarity, this remains highly speculative. There exists not a single shred of direct evidence confirming artificial origin for 3 Atlas. No radio transmissions have been detected, no unmistakably manufactured materials identified, and no unambiguous technological signatures observed. What remains are peculiar behavioral patterns that prove difficult to reconcile with known natural processes on planetary bodies. These same behaviors, while still unproven, appear slightly more readily explicable through the lens of engineering principles. This does not, however, constitute definitive proof of extraterrestrial craftsmanship. This observation does not constitute compelling proof. It remains a theoretical proposition, one plausible interpretation of the gathered information, yet merely one among several potential explanations. Furthermore, accepting this idea would necessitate embracing extraordinary assertions, claims which fundamentally demand correspondingly extraordinary evidence. Regrettably, such definitive evidence remains elusive at present. Despite its tentative nature, this line of speculation holds significant value. Its importance stems not from any likelihood of its truth, but rather from its unique capacity to compel intellectual rigor. It forces us to confront our observations with unprecedented clarity. This perspective demands that we pose more precise, pointed inquiries. If this phenomenon were indeed artificial in origin, what specific signatures or anomalies would we anticipate detecting? How could we conclusively differentiate such an artificial construct from a naturally occurring celestial body? What precise observations would definitively disprove the artificial hypothesis? Contemplating these questions sharpens our analytical tools and refines our scientific approach, regardless of whether the final explanation proves to be disappointingly ordinary or mundane. Consider this profound realization that occupies the minds of many astronomers. Even if Oumuamua is later confirmed to be entirely natural, even if every observed behavior finds a perfectly prosaic, conventional explanation we have simply yet to uncover, the very fact that we are engaged in this profound conversation signifies a fundamental shift. It signifies that we have arrived at an unprecedented juncture in astronomy. artificial objects now reside within the scientifically plausible spectrum of possibilities we seriously entertain. The question, could this be evidence of technology, has transitioned from being considered scientifically frivolous to a legitimate, albeit challenging, area of inquiry. This represents a profound threshold, one that we have genuinely crossed. Whether or not this particular interstellar visitor ultimately substantiates that threshold, the very fact that we find ourselves at this pivotal moment formulating these questions marks a revolutionary shift in our collective understanding of the cosmos and our place within it. This evolving perspective forms the foundation for contemplating a radically different universe. Part 10, Alternative Cosmos. Specifically, it explores what Oumuamua suggests about the fundamental possibilities existing beyond our solar system. Let us momentarily set aside the captivating speculation regarding artificial origins. For a moment, let us wholeheartedly assume that Oumuamua is entirely natural. The initial premise doesn't eliminate the enigma, it fundamentally redirects it. If this phenomenon occurs naturally, arising from cosmic processes entirely devoid of intelligence, then our conceptual framework regarding the possibilities inherent within the vast emptiness between stars has been profoundly limited. Consider the debris generated by a supernova. The detonation of a colossal stellar body transcends mere dispersion of gaseous remnants. It acts as a cosmic furnace, synthesizing copious quantities of dust.
This material encompasses carbon compounds, silicate minerals, metallic iron, and intricate organic molecules, all precipitating from the superheated plasma of the expanding fireball within the critical days and weeks following the cataclysm. This newly forged dust subsequently permeates across light years, integrating into the galactic interstellar medium before becoming incorporated into nascent planetary systems. However, a significant portion may coalesce into larger entities prior to this widespread dispersal. Imagine nascent aggregates of freshly synthesized dust still radiating residual heat from their explosive genesis, sculpted by intense shock waves into architectures fundamentally distinct from those formed through slow, incremental accretion over eons. These objects would represent infants within the cosmic timescale, possessing an age measured in mere millions of years, not the billions characteristic of established celestial bodies. Their chemical signature would be a direct imprint of their violent origin, reflecting the specific elements and compounds ejected during the supernova event. Expect concentrations of heavier elements, complex carbon chains, and isotopes considered exotic or absent within typical solar system objects formed under gentler conditions. Furthermore, the extreme environment of their creation likely imbued them with unusual internal characteristics. Magnetic fields present during formation could become permanently embedded within the dust matrix itself. Compositional variations might establish distinct electrical interfaces throughout their structure. Internal voids and chambered cavities could form, potentially serving as reservoirs capable of trapping residual gases or electrical charges. Such entities would bear no resemblance to comets, which develop gradually and peacefully within the quiescent environments of protoplanetary disks. Children exhibiting violent tendencies often manifest corresponding destructive behavior. Similarly, consider the profound transformations possible within carbonaceous matter subjected to intense radiation over immense timescales. Scientists understand that complex organic molecules existing throughout the vastness of space undergo significant alteration due to relentless cosmic rays, intense ultraviolet radiation, and the gradual buildup of radiation damage accumulated over hundreds of millions of years. These persistent energy bombardments can fundamentally alter a material's characteristics in unexpected and surprising ways. For instance, substances that were once inherently brittle may become pliable and viscous. Electrical insulators can transition into conductors. Highly ordered crystalline structures can devolve into disordered amorphous states. If the colossal entity known as 3I Atlas is constructed from such responsive materials, and if it has endured exposure to the harsh interstellar radiation environment for hundreds of millions of years, its observed behavior could very well reflect unique states of matter that have never before been replicated or studied within terrestrial laboratories. Furthermore, the concept of long-distance magnetic coherence presents another fascinating possibility. The interstellar medium, far from being truly empty, is permeated by an extremely diffuse plasma intricately threaded through with complex magnetic fields. Objects traversing this pervasive environment for durations measured in hundreds of millions of years might, over such epochs, acquire a subtle but significant magnetization. This magnetization would not be overwhelmingly strong, yet its cumulative effect over eons could become critically important. Astronomical observations show that individual dust grains can naturally align themselves along the direction of prevailing magnetic fields. Imagine a vast, loosely bound cloud of partially magnetized dust grains held together by the weak force of gravity. Within this cloud, the intricate magnetic interactions occurring between adjacent grains could potentially sculpt large-scale structure. Regions might emerge where the magnetic fields harmoniously align, juxtaposed against boundaries where opposing fields create distinct interfaces. The ultimate result could be the formation of a celestial body behaving more like a sophisticated magnetic composite material than merely a disorganized pile of cosmic dust. This specific line of reasoning naturally leads to the intriguing theoretical framework known as the electrostatic comet concept. This is an idea that some theoretical physicists have explored and developed through mathematical models and simulations, yet it remains entirely unobserved within our actual astronomical observations to date. Imagine an object where the repulsive force between charged dust particles acts as a counterbalance to the gravitational pull. This means that although the object remains cohesive, it does so by the thinnest of margins. Within this structure, the influence of electromagnetic forces is as significant as that of the object's mass. Such an entity would be delicate and susceptible to disruption, yet it could also undergo abrupt restructurings. When the surrounding environment changes, be it through increased intensity of the solar wind or alterations in the direction of magnetic fields, the equilibrium of forces within the object is perturbed. The distribution of electrical charges shifts, material is displaced, jets emerge. These are not unfounded speculations, they are extrapolations of established physical principles applied to realms beyond our current exploration. Each component of this scenario exists independently somewhere in the cosmos. We've observed the effects of charge in dust.
We've identified magnetic fields in space. We've witnessed intricate organic chemistry within interstellar clouds. What remains unobserved is the convergence of all these phenomena within a single entity. Yet, why wouldn't such a combination exist? The universe is vast. It has had billions of years to experiment with combinations. Some of these combinations might yield objects that seem impossible until one realizes that they have simply not observed this particular mix of circumstances before. There lies the philosophical inquiry underlying all this. How much of what exists out there have we truly sampled? We've scrutinized a few hundred comets thoroughly. We've examined meteorites originating from perhaps a few dozen parent bodies. We've witnessed to count them, three confirmed interstellar visitors. That is not a representative sample. Observing only 3 celestial objects represents merely the most tentative threshold of understanding. It is akin to attempting to grasp the staggering complexity of terrestrial biodiversity by examining just 3 disparate life forms. One might, for instance, encounter a small rodent, a common bird, and a pond dweller, before concluding that all animals are diminutive, largely benign, and perhaps even unremarkable.
Such a limited vantage point would inevitably overlook the vast spectrum of existence, including creatures of immense scale, like the elephant, organisms of extraordinary intelligence, such as the octopus, or colossal structures, like the redwood tree. The object designated 3 Atlas might therefore stand as the elephant inhabiting our cosmic living room. The significance does not primarily stem from any artificial origin, but rather from its potential representation of a fundamental category of cosmic entity that humanity has simply never encountered or sampled. It is entirely plausible that the interstellar medium teems with such phenomena. These could be vast aggregates of charged dust particles, magnetically active formations possessing complex electromagnetic properties, or carbonaceous structures exhibiting entirely unprecedented characteristics. These entities likely drift silently through the space between stars, remaining utterly undetectable until one serendipitously passes sufficiently close to a solar system where their presence might become apparent. Humanity has now encountered 3 such objects, each displaying distinctly different properties, defying easy categorization. This divergence in observations should not provoke surprise, but instead ignite profound excitement. If confirmation establishes 3 Atlas as belonging to an entirely new class of astronomical object, the ramifications for the field of astronomy would be transformative. It would immediately signal that our current models governing the formation and evolutionary processes of small celestial bodies are fundamentally incomplete.
This revelation would catalyze the opening of entire new frontiers in research, encompassing the intricate physics of cosmic dust, the complex dance of plasma interactions, and the study of electromagnetic structures manifesting within the vastness of space. Furthermore, it would necessitate a thorough reevaluation of our expectations for future spacecraft missions dispatched to explore other star systems. This would serve as a powerful reminder that nature possesses a creativity far exceeding the boundaries of our existing theoretical frameworks. Nevertheless, should subsequent investigation reveal that 3 Atlas proves to be something far more mundane, potentially attributable to our earlier misinterpretation stemming from insufficient data, such an outcome would also represent valuable progress within the scientific endeavor. Progress in science often emerges not only from triumphs, but equally from missteps. Each incorrect hypothesis discarded propels us nearer to the accurate explanation. The vital aspect lies in our willingness to pose questions, to entertain perspectives beyond our established frameworks, and to avoid becoming so devoted to current models that we disregard the evidence presented by empirical data. This is the fundamental reality. The cosmos operates independently of our conceptual frameworks. Celestial bodies ignite, evolve, and cease to exist without reference to academic literature. Planetary entities traverse their trajectories, engage in collisions, and occasionally are expelled into the vast emptiness. Microscopic particles coalesce, drift through voids, and at times spontaneously arrange into formations whose names remain unknown to us. Rarely, but occasionally, portions of this material draw sufficiently near to our location to permit detailed scrutiny. These instances hold immense value. They function as portals into the immense universe, the realm inaccessible to direct travel, existing autonomously from human perception and comprehension. The 3 Atlas observation represents one such portal. Whether unveiling novel physical principles, introducing previously unknown categories of celestial bodies, or revealing phenomena even more enigmatic than anticipated, the perspective offered is breathtaking. However, consider this surprising revelation. 3 Atlas does not stand alone as an unprecedented portal opened this year.
2050 has witnessed an extraordinary accumulation of anomalies, observations that defy conventional expectations, and minor enigmas emerging across diverse scientific disciplines. When viewed collectively, these disparate occurrences suggest a discernible pattern. This pattern signifies neither a hidden agenda nor a deliberate design, but rather serves as a poignant reminder that humanity currently inhabits an epoch characterized by authentic, groundbreaking discovery.
A profound sense of intellectual tension, the very kind that emerges when one stands precariously at the threshold of comprehension. It is the unsettling feeling when sophisticated instrumentation reveals phenomena just beyond the grasp of theoretical frameworks. This particular state of inquiry marked the 11th chapter of investigation. The chronometer read November 25th. The phenomenon under scrutiny bore the provisional designation of the quantum gravity micro-resonance anomaly. While celestial observers in the astronomical community grappled with the enigma of 3 celestial bodies appearing simultaneously within the nocturnal firmament, a parallel intellectual challenge unfolded within a high-security laboratory nestled in the outskirts of Geneva. Researchers there were confronted by data from an experiment meticulously engineered to probe the boundaries of quantum mechanics when applied to gravitational fields. The results obtained defied established principles, revealing behaviors theoretically impossible. The experimental apparatus itself represented a triumph of precision engineering. Ultra-cold atoms, chilled to temperatures within 1/millionth of a degree above absolute zero, were suspended within a meticulously constructed optical cavity. This setup achieved near-perfect isolation, effectively shielding the atoms from vibrational disturbances and extraneous electromagnetic interference. The primary objective was unequivocal: to measure with unprecedented accuracy the subtle alterations in quantum states induced solely by the constant presence of Earth's gravitational field. What the researchers recorded, however, diverged radically from expectations. Instead of a stable measurement, they observed a persistent, minute drift in the fundamental resonance frequency of the cavity. This shift manifested unpredictably, appearing and disappearing without discernible pattern. Initial reactions centered on potential error. Such experiments operate at the extreme limits of technological capability, making them vulnerable to myriad confounding factors. Minute thermal expansion or contraction of the experimental apparatus itself, the presence of faint electromagnetic fields generated by the complex array of nearby laboratory equipment, or even subtle gravitational perturbations caused by vehicles passing on the street outside. Each possibility presented a plausible, though vexing, explanation for an anomalous signal. The research team dedicated weeks to exhaustive verification. They performed meticulous recalibration of all instruments. They enhanced the electromagnetic shielding surrounding the experiment. Crucially, they conducted control runs without the atoms present, solely to quantify the baseline background noise inherent to the apparatus and environment. Despite these rigorous efforts, the elusive frequency drift persisted.
It did not manifest continuously, but its occurrence was frequent enough to rule out mere coincidence or a single undetected source of error. The phenomenon proved profoundly puzzling. Its drift showed no correlation with any known factor. It defied explanation through local gravitational fluctuations, cosmic ray intensity variations, lunar tidal influences, or terrestrial seismic events. While initially appearing as pure randomness, rigorous statistical evaluation revealed an underlying order within the apparent chaos. Hidden structures emerged from the noise, suggesting a consistent, unidentified causal mechanism. This unsettling possibility ignited passionate discussion among theoretical physicists. Some cautiously proposed it could constitute the very first tangible experimental evidence for effects predicted by quantum gravity theories. The fundamental premise holds that gravity itself must ultimately be quantized, originating from quantum processes currently beyond human comprehension. Conventional quantum gravity models, however, consistently forecast that such phenomena would only manifest under conditions of extreme energy levels or infinitesimally small spatial scales, firmly out of reach of existing technological capabilities. A minority of alternative theories, nevertheless, posited the existence of minuscule, detectable signatures within ultra-precise laboratory measurements. These might reveal a subtle fuzziness inherent to space-time itself, potentially manifesting as anomalous noise in highly controlled experimental setups. Opposing voices within the scientific community emphasized alternative explanations, lingering calibration errors, unaccounted environmental disturbances, or statistically improbable flukes destined to vanish with increased data sets. Consequently, the debate remains vigorous and unresolved. Academic papers are currently under development, and replication studies are actively being scheduled across multiple research laboratories worldwide. This cautious, skeptical, and meticulously verifiable process exemplifies the scientific method when confronted with unexpected anomalies. Yet, this episode carries particular significance within the broader narrative of discovery. Historically, seemingly insignificant anomalies have frequently acted as catalysts, leading to the emergence of entirely new scientific disciplines and fundamentally reshaping our understanding of the universe. Before quantum mechanics gained acceptance, scientists grappled with perplexing spectral lines appearing in atomic emissions. These subtle discrepancies defied explanation within the framework of classical physics, yet their reality was undeniable. For 10 decades, they eluded understanding until a fundamental revolution in thought transformed these anomalies into the bedrock of an entirely new comprehension of matter and energy.
This historical pattern serves as a profound reminder. Phenomena dismissed as mere background noise today might one day constitute vital signals revealing deeper truths tomorrow. The observed behavior of 3I Atlas could represent a macroscopic manifestation of this very type of misunderstood physics. Just as the cavity experiment seeks to probe the elusive intersection where quantum mechanics meets gravity, 3I Atlas might be exploring unique conditions where the complex dance of dust dynamics intertwines with electromagnetic forces in manners previously unmodeled. Both scenarios exist at the fringes of known physics, producing data that resists incorporation into existing theoretical frameworks. Both stand as potent reminders of the inherent incompleteness in our current understanding of the physical world. The parallel runs even deeper. In both phenomena, we observe behaviors that appear intermittent, seemingly switching on and off without any discernible trigger, operating under rules that elude recognition. The frequency drift witnessed in the cavity experiment finds a striking counterpart in the episodic jet activity emanating from 3I Atlas. Both suggest underlying processes are occurring that our current models simply do not account for. While it is highly improbable that the specific mechanisms are directly related, charge dynamics within dusty plasmas sharing identical mathematical structures with quantum fluctuations within gravitational fields, the core significance lies in the connection itself. Discovery rarely unfolds in isolation. Profound breakthroughs achieved in one field frequently cast illuminating light on problems persisting within another, demonstrating the interconnected nature of scientific progress. Scientific breakthroughs rarely announce themselves with fanfare. Their origins are often more subtle, emerging instead from persistent, uncomfortable data points. These are results that demand meticulous rechecking, observations stubbornly refusing to conform to established frameworks. History provides compelling illustrations of this pattern. When scientists first meticulously measured the pervasive cosmic microwave background radiation, their initial reaction was to suspect
contamination, specifically the unwelcome presence of avian droppings obscuring their antenna signal. Similarly, astronomers detecting the highly regular pulses of the first known pulsar entertained the fantastical possibility of extraterrestrial communication before settling on a more terrestrial, albeit revolutionary, explanation. In both foundational cases, the immediate instinct was to attribute the anomaly to error or misinterpretation, resisting the profound implication that a genuine, unprecedented phenomenon had been discovered. Present-day science faces analogous moments of profound incongruity. The phenomenon referred to as the 3-2 Atlas represents precisely such inconvenient data.
It defies easy categorization, resisting integration into current theoretical models. Every proposed explanation demands stretching the principles of known physics to their very limits, resulting in models that feel fundamentally strained. Yet history compellingly suggests that such moments of deep tension are precisely when discovery becomes most thrilling. Paradigm shifts seldom occur by design. They are compelled by the immutable insistence of reality itself. This year's unfolding events powerfully reinforce a crucial lesson. Reality consistently possesses greater complexity and ingenuity than humanity has thus far acknowledged. The quantum gravity anomaly stands as one stark example of this principle. The 3-2 Atlas anomaly constitutes another. They are demonstrably not isolated incidents. Examining the broader scientific literature reveals a discernible pattern emerging. Part 12 of this unfolding saga involves an artificial intelligence system operating throughout August of 2025 designed specifically for analyzing the atmospheres of distant exoplanets. This system identified a signature, an atmospheric composition flagged as highly improbable, existing in defiance of expectations and challenging established astrophysical models. The Advanced Artificial Intelligence System was meticulously analyzing data streams from the James Webb Space Telescope. Its focus was on transit spectroscopy readings gathered for a particular world, a warm Neptune-sized planet designated K2-318b. This celestial body orbits a star located 100 light-years from Earth. Within the vast catalog of discovered worlds, K2-318b presented itself as rather unremarkable. It was a mid-sized planet, experiencing moderate warmth, positioned perilously close to its host star. Consequently, it fell outside the zone where liquid water could potentially exist, ruling out habitability. Yet it also resided far enough away to avoid being completely stripped of its atmosphere or torn apart by stellar forces. Such planets were considered standard examples, numerous like it cataloged across the galaxy. The AI's sophisticated atmospheric retrieval algorithm, having been trained on the spectra of thousands of previously studied exoplanets, identified a profound inconsistency within K2-13b's data. The planet's atmosphere displayed clear signatures of both carbon dioxide and ammonia. However, these two gases appeared to engage in a peculiar cyclical dance. Concentrations of carbon dioxide would demonstrably increase while ammonia levels decreased. Then the pattern would effortlessly reverse itself. This fluctuation occurred predictably over the course of the planet's entire orbit, repeating with remarkable consistency each time it completed a circuit around its star. Human experts in atmospheric chemistry reviewed the data flagged by the AI and were left genuinely perplexed.
There exists no established chemical principle within our current understanding that predicts this specific inverse behavior between carbon dioxide and ammonia. This phenomenon simply does not occur in the atmospheres of gas giants, as far as known science is concerned. These two molecules are not competing for the same chemical resources. Crucially, they do not act as products and reactants within a reversible reaction mechanism capable of generating such an inverse cycle. Logically, based on known atmospheric dynamics, both gases should respond similarly to environmental changes. They would be expected to fluctuate in tandem, influenced primarily by the shifting temperatures and pressures encountered as the planet journeyed through its elliptical path around the star. The observed inverse relationship defied established chemical expectations. The research team meticulously processed the data using conventional atmospheric modeling frameworks, specialized chemistry software, and rigorous thermodynamic calculations. Every standard analytical tool planetary scientists employ to decipher the composition and behavior of worlds orbiting distant stars. Yet astonishingly, none of these established methods could replicate the distinctive pattern revealed in the observations. The models projected either persistently stable concentrations for both gases or wildly erratic fluctuations that bore no resemblance to the remarkably regular, rhythmic oscillation actually detected. This precise phenomenon of clean, anti-correlated oscillation remained elusive to conventional simulation. The true significance of this discovery lies in how it fundamentally challenges previous analytical approaches. Human scientists had previously reviewed this very dataset. A preliminary examination conducted months prior had indeed identified the mere presence of both gases, yet it had completely overlooked the critical, dynamic relationship between them, the cyclical dance of their concentrations rising and falling in opposition. The breakthrough emerged because artificial intelligence was explicitly programmed to hunt for patterns imperceptible to human observers. Its algorithms actively sought correlations buried deep within noise, identified subtle periodicities that would remain hidden from the human eye scanning spectra visually. It is crucial to understand that this achievement does not imply artificial intelligence possesses inherent intellectual superiority over human researchers. Rather, its strength stems from a unique form of patience and exhaustive diligence. The AI possesses the unfailing capacity to systematically evaluate thousands, even tens of thousands of potential correlations without fatigue, boredom, or the unconscious bias of assuming what factors might prove significant. This relentless, unbiased scrutiny uncovered a dimension of atmospheric behavior that human analysis had systematically failed to perceive.
This success compels the sobering realization of how much scientific understanding may have been inadvertently overlooked. It prompts uncomfortable questions. How many other exoplanetary atmospheres harbor similarly peculiar, intricate patterns that have simply escaped detection because researchers weren't actively searching for them? How many subtle anomalies lie dormant within vast scientific archives, waiting for an observer, human or artificial, to finally recognize their significance? The AI's triumph in revealing this hidden complexity strongly suggests that human scientific practice has, until now, maintained a systematic blindness towards certain types of atmospheric phenomena. The parallel to the discovery associated with 3I Atlas becomes strikingly apparent within this context.
We have persistently attempted to explain its behavior using static models and equilibrium calculations. Yet the object itself unmistakably demonstrates that it is not, in fact, in a state of equilibrium. The cosmic environment is not static. It is a dynamic entity, perpetually shifting through various states and responding instantaneously to its surroundings. This ongoing transformation is prompting a new wave of scientific inquiry. Some researchers now propose a novel approach, leveraging artificial intelligence assistance to help decipher the mysteries surrounding the interstellar object designated as 3I-Atlas. The method involves feeding an advanced neural network an immense volume of observational data, encompassing detailed brightness curves, comprehensive spectroscopic measurements, precise jet timing information, and every other relevant data set available. By doing so, the AI could autonomously search for complex patterns. These patterns might correlate with critical environmental factors such as solar wind conditions, intricate interplanetary magnetic field data,
and fluctuating cosmic ray flux levels. There exists a possibility that crucial relationships remain undiscovered simply because conventional analysis hasn't examined the correct combinations of these numerous variables. The discovery of the intricate atmospheric composition orbiting the distant world K2318b, located 200 light-years from Earth, provides compelling evidence. It demonstrates that planetary complexity extends far beyond the boundaries of our current theoretical frameworks. This finding proves that planets can exhibit behaviors and properties that genuinely surprise us. It reveals that the interplay between complex chemistry and extreme environmental conditions can generate phenomena we had not anticipated. If a hot Neptune, situated 200 light-years from Earth, can defy our expectations in its actions and characteristics, why should we assume that an interstellar visitor, originating from another star system and now passing through our own solar system, adheres strictly to our preconceived notions? Why should we presuppose that 3I-Atlas is constrained by the physical laws as we currently understand them? Our scientific journey has consistently shown that whenever we believe we have uncovered fundamental physics, new discoveries emerge that challenge and expand our comprehension. This theme of encountering profound surprises and the failure of established models is becoming increasingly apparent across numerous scientific disciplines this year. We are witnessing expectations being violated, theories collapsing under the weight of new observations, and data that compel a fundamental reconsideration of what we believed we knew. Importantly, these paradigm shifts are not occurring in obscure theoretical corners of science. They are unfolding within mainstream observations, during flagship space missions, and in well-funded, rigorous experiments.
The universe appears to be communicating its truths with remarkable clarity. The challenge lies in our current inability to fully comprehend this language. However, history teaches us that sometimes the most profound messages, the revelations that fundamentally reshape our understanding, originate from the most unexpected places. Contrary to expectations often held for life's distant frontiers, exotic exoplanets, or enigmatic quantum realms, the astonishing discovery originated remarkably close to home. It emerged from Earth's own most forbidding undersea depths, environments previously presumed utterly unsuitable for biological existence. The stage was set in March of this current year. A specialized drilling operation delved into the Philippine Sea, achieving an unprecedented feat. Researchers retrieved cylindrical samples of oceanic crust from a staggering 12 kilometers beneath the sea floor. This represented a vertical journey deeper than any human expedition had ever successfully penetrated into the planet's crust. It surpassed the boundaries of conventional scientific exploration, venturing into territory long considered a biological void. The conditions at such profound depths are exceptionally hostile. The pressure encountered is immense, exerting a crushing force thousands upon thousands times greater than the air pressure experienced at the surface. Despite the insulating blanket of miles of water and rock above, temperatures approach boiling point, creating an environment that would denature proteins and disrupt cellular structures. Furthermore, sunlight cannot penetrate this abyss. Oxygen is entirely absent. This combination renders the location approximately as inhospitable to life as any place on Earth could possibly be. Once extracted, the core samples remained undisturbed within a laboratory setting for several weeks. This period allowed researchers to meticulously prepare for analysis, following rigorous standard protocol. The procedure began with carefully sterilizing the outer surface of each core segment. This crucial step aimed to eliminate any potential contamination introduced by the drilling fluids used during retrieval. Subsequently, the sterilized cores were carefully cracked open within a strictly controlled clean room environment.
Scientists then extracted material from the pristine interior sections. The primary objective was to scrutinize these samples for any evidence of biological activity. Initial expectations were remarkably low. Researchers anticipated perhaps discovering a few inert microbial spores, remnants of ancient organic material that might have slowly settled down from much shallower ocean layers over millions of years, or potentially finding absolutely nothing at all. What they encountered fundamentally altered scientific understanding. Embedded deep within the Earth's crust at 12 kilometers down, under conditions that should have precluded any biological processes, were living microbes. These organisms were not merely dormant survivors clinging to existence, nor were they barely alive. They exhibited clear metabolic activity, actively reproducing and deriving energy directly from complex chemical reactions occurring between the surrounding rocks and the trapped water. They were engaged in building new biomass, maintaining intricate cell walls, and performing the essential biological functions that characterize life, all while enduring the relentless pressure and extreme heat that should have destroyed them. This discovery challenged fundamental assumptions about the very limits of life on our planet. The revelation fundamentally reshaped biological science's perception of life's resilience. Previously, scientists held firm convictions regarding biological boundaries. Temperature, for instance, was believed to possess rigid thresholds dictated by the inherent instability of organic molecules under extreme heat or cold. Pressure seemed equally constrained, governed by the physical limits of cellular structures. Compress too forcefully, and vital membranes would inevitably rupture. Furthermore, energy availability imposed a critical threshold, suggesting that environments too sparse in usable resources would be unsustainable, as the metabolic cost of existence would surpass the energy that could be harvested. These were not flexible suggestions, but immutable laws, dictated by the unyielding principles of physics and chemistry. Yet, organisms were discovered actively thriving precisely within these purportedly forbidden zones, seemingly disregarding constraints previously considered absolute. This finding sent ripples far beyond the field of biology. If life could persist at depths of 12 kilometers within our planet's own crust, subjected to crushing pressure and complete isolation from the sun's energy, what other locations in the vast cosmos might potentially harbor life? Could organisms exist within the immense, lightless oceans concealed beneath the icy shells of Jupiter's moon Europa? Or perhaps within the hidden reservoirs suspected on Saturn's moon Titan? Could life persist within deep aquifers, potentially harboring liquid water that scientists once deemed sterile wastelands because their conditions violated our established notions of what life requires? This discovery does not constitute proof of extraterrestrial life, but it profoundly broadens the spectrum of environmental conditions we must seriously contemplate. It shifts the very target we are aiming for. This episode offers a profound lesson concerning extremity and the capacity for the unexpected. When systems are pushed into the most severe and unnatural conditions, their behavior often defies predictions derived solely from studying them under normal, everyday circumstances.
Water, familiar to us under standard atmospheric pressure, exhibits specific well-known properties. However, subjected to immense pressure, water transforms, adopting entirely different crystalline structures and gaining the ability to dissolve materials it normally would not. The same principle applies universally. Chemical reactions accelerate or change course unpredictably, material properties alter dramatically, and essentially every physical process behaves in ways fundamentally distinct from its behavior in commonplace environments. The universe, it seems, holds unexpected surprises when pushed to its limits.
Attempting to project knowledge from one environmental regime onto another is inherently perilous. The natural world operates without regard for our analytical frameworks. It simply is. The object designated Oumuamua inhabits an environment of exceptional harshness. While this might not qualify as extreme on a stellar scale, it represents the ultimate frontier for smaller celestial bodies. This interstellar traveler originated beyond the boundaries of our solar system, having been exposed to radiation environments utterly alien to our local cosmic neighborhood. Its physical characteristics may well have been sculpted by conditions entirely absent within our own planetary system. When such an object ventures into the inner solar system, subjected to the relentless bombardment of solar winds and intense radiation, why should we anticipate it behaving similarly to bodies that formed tranquilly within the protoplanetary disk? The extremophile microorganisms thriving in Earth's deepest ocean trenches serve as our planet's direct equivalent to these interstellar visitors. They are exquisitely adapted to conditions we rarely encounter, harnessing chemical processes fundamentally unfamiliar to conventional observation, and flourishing in environments our established models deemed physiologically impossible. Their very existence instills profound humility. They serve as a constant reminder that our scientific understanding is constructed upon a remarkably limited sampling of viable conditions across the universe. This necessitates the recognition that the cosmos itself is vaster and more enigmatic than our current theories can encompass. Furthermore, it underscores the critical danger inherent in presuming limitations on what is possible, a path that swiftly leads to scientific error. This recurring theme of astonishing resilience and adaptability permeates the natural world. Life forms persist in the face of radiation levels proven lethally fatal to most known organisms. Materials retain their structural integrity at temperatures sufficient to liquefy them under standard terrestrial conditions. Chemical reactions proceed at rates considered unattainable without the presence of catalysts. Each time our observational reach extends into previously unexplored regimes, we encounter revelations that challenge established paradigms.
Observations in science are not occasional surprises, but rather routine occurrences demanding our attention. Consequently, when we examine our third interstellar visitor, it seems inevitable that we should encounter unexpected phenomena. This anticipation parallels a remarkable discovery from the depths of our own planet's oceans. The significance of direct observation, as demonstrated by deep-sea exploration, cannot be overstated. Prior to the ambitious drilling project targeting extreme depths, prevailing scientific models confidently predicted that no form of life could possibly exist at such immense pressure. These models rested upon solid foundations of established physics and chemistry, incorporated reasonable assumptions about cellular metabolism, and appeared logically sound. Yet these very models proved fundamentally incorrect. The error did not stem from flaws in the underlying physics. The problem lay in the models themselves being incomplete. They failed to account for alternative metabolic pathways utilized by pressure-adapted proteins. They overlooked the existence of organisms possessing evolutionary solutions to problems humanity had never recognized as solvable. We stand in a comparable position regarding the object designated 3 Atlas. Current scientific models indicate that observable jets should not exist without the presence of gas. These models are constructed upon credible physics, informed by centuries of comet observations, and grounded in reasonable assumptions about sublimation processes and dust dynamics. However, it remains possible that these models are incomplete. Perhaps alternative mechanisms operate beyond our current understanding. Maybe the object possesses unique physical properties that our existing frameworks simply do not account for. The only definitive path forward is persistent observation, continuous data collection, and rigorous testing of even the most seemingly improbable hypotheses.
This approach is essential because here lies a profound truth about extreme environments. They teach us that nature possesses a creativity surpassing our own. Solutions exist to problems we previously believed were unsolvable. The boundaries we establish around what is considered possible often reflect the limitations of our current knowledge more than the true capabilities of the natural world. The resilient microbes discovered at 12 kilometers below the ocean's surface existed regardless of the theoretical impossibility declared by earlier models. Their actions simply occurred. The Atlas system displayed no awareness of any transgression against our scientific models. It merely existed and operated as it was designed. Consequently, the responsibility for comprehension fell upon us, the scientists. Our fundamental duty, however unusual the observed reality might prove to be, is to diligently investigate the underlying cause.
The objective is to progressively refine and broaden our explanatory frameworks until they accurately encompass even the most perplexing aspects of nature. Yet, the phenomenon of unexpected behavior extends far beyond our laboratories. It even manifests upon our closest celestial neighbor, the very star that dominates our solar system, the object we understand most intimately across the cosmos after our own world, has exhibited astonishingly erratic patterns this year. Consider the solar surface anomaly designated as the butterfly void. This event, revisited in new analysis, first captured astronomers' attention during the month of October. Solar observers were bewildered by the sudden emergence of a vast, magnetically inert zone covering an area approximately 50,000 kilometers across upon the Sun's surface. The solar photosphere, ordinarily characterized by a dynamic and turbulent network of magnetic field lines, constantly in flux as they shift, twist, and explosively reconnect, giving rise to sunspots, violent flares, and towering coronal loops, presented this stark anomaly. Within this specific region, the magnetic field intensity plummeted to near absolute zero. Intriguingly, regions of active magnetic phenomena actively steered clear of this quiet expanse. This profound stillness persisted for roughly 18 hours before exhibiting a gradual return to the Sun's typical vigorous magnetic activity. At the time, researchers coined the term butterfly void for this phenomenon. The name reflected both its distinctive shape, vaguely reminiscent of butterfly wings, and its nature as a void, a significant absence within the normal pulsating tapestry of magnetic activity. Initial interpretations suggested this occurrence was a rare, though naturally occurring fluctuation within the Sun's complex behavior. Some hypothesized a possible connection to the cyclical nature of solar activity or to unseen flows of plasma deep beneath the visible surface. Several scientific papers were subsequently published detailing the event. The solar physics community acknowledged this as a particularly noteworthy and unusual occurrence, cataloging it within their records before naturally shifting focus to subsequent observations. Then, during the following month of November, fresh magnetic imaging data collected by multiple observatories actively monitoring the Sun during the void's occurrence became available for further scrutiny. Through enhanced observational techniques yielding higher resolution imagery, smoother data rhythms, and the measurement of additional spectral lines, scientists re-examined the enigmatic butterfly void within the Sun's magnetic field. This renewed analysis unveiled a critical insight previously overlooked. The void's occurrence was not a random phenomenon. Instead, it demonstrably aligned with distinct alterations in the solar wind emanating from that specific solar region.
The solar wind streaming from within the butterfly void exhibited anomalous characteristics, significantly lower particle density, notably higher velocity, and unusual ratios of elemental composition compared to standard solar wind flows. This discovery holds profound implications. The solar wind directly interacts with and shapes the environment throughout the inner solar system. Our planet's protective magnetosphere dynamically responds to variations in this constant stream of charged particles. Comet tails, those iconic features trailing away from their stellar source, are sculpted and directed by prevailing solar wind patterns. Furthermore, smaller celestial bodies possessing significant electrical charge or inherent magnetic properties would inherently react to these subtle environmental shifts. The possibility arises that if this particular butterfly void event wasn't an isolated occurrence, but rather an indicator of a broader, more frequent phenomenon, where similar localized magnetic field collapses happen regularly, then their cumulative effect could be significant. These events, potentially too fleeting or too confined in spatial scale to be readily detected individually, might collectively generate variable conditions. These fluctuating solar wind properties could, consequently, influence the behavior and activity of various solar system objects in ways not yet fully understood. This line of inquiry finds intriguing relevance in the study of Comet 3 Atlas. Its dramatic outbursts of material or jet activity do not follow a perfectly predictable pattern directly tied to its orbital distance from the Sun or its rotational cycle. However, emerging preliminary data suggests a potential link between these outbursts and variations within the solar wind itself. There are indications that episodes of heightened jet activity might occur more frequently when solar wind speeds increase or when the orientation of the solar wind's embedded magnetic field undergoes specific shifts. While the correlation isn't absolute and could potentially stem from coincidence, the suggestive patterns warrant dedicated investigation. Here, the analysis transitions into more profound territory. This research fundamentally challenges a simplistic view. The Sun transcends the role of merely a stable, distant light source illuminating the solar system. It emerges as a dynamic, influential force whose internal processes and variable emissions actively sculpt the environments and behaviors of planets, comets, and countless smaller bodies within its domain. This celestial body operates with remarkable dynamism, actively shaping a perpetually shifting electromagnetic landscape. Most astronomical objects remain largely impermeable to these fluctuating forces. Rocky planets, for instance, enjoy the protective embrace of magnetospheres that deflect harmful solar influences.
Gas giants, owing to their immense mass, possess gravitational fields strong enough to mitigate significant electromagnetic perturbations. However, comets, characterized by their relatively small size, tenuous cometary envelopes, and exposed surfaces, find themselves particularly vulnerable at the frontier where solar wind effects become critically significant. An object such as the interstellar comet 3I ATLS, if it exhibits heightened sensitivity to electromagnetic conditions, might be responding to variations in the solar wind through mechanisms unlike those typically observed in other bodies. The re-examination of the butterfly void phenomenon revealed that even concerning our closest stellar neighbor, the Sun, a subject of constant surveillance through specialized telescopes, we routinely overlook subtle phenomena. We misrepresent the nature of events. We fail to appreciate the true extent of variability present. If such significant observational gaps exist regarding the Sun, how much more profound must our limitations be when observing distant stars whose energetic outbursts we detect only sporadically? How much more uncertain are our assumptions about exoplanet systems, where we often rely on a single transit observation and extrapolate it to represent the system's typical conditions? how much more speculative become our understanding of the interstellar medium, whose fundamental properties we attempt to deduce from sparse and incomplete measurements. Furthermore, the solar data prompts a fundamental question about causation. When 3I ATLS generates jets of material, is its behavior driven entirely by internal processes, or does it react to external triggers? The solar wind represents one potential catalyst. Variations in cosmic ray flux constitute another. The specific orientation of the local magnetic field could serve as a third factor. Fluctuations in temperature resulting from the changing intensity of solar illumination provide a fourth. Crucially, all these environmental factors undergo change over timescales that could align precisely with the observed cycles of jet activity. What becomes apparent when considering 3I Atlas as an exceptionally sensitive electromagnetically reactive instrument is that its observed jets likely convey crucial information about the surrounding space environment itself, often revealing more about those local conditions than about the object generating the jets. This recurring pattern underscores a fundamental principle. Many observed phenomena are inherently observer-dependent. The outcome of the quantum cavity anomaly fluctuates based on the precise moment of measurement. The composition detected within exoplanet atmospheres shifts depending on their specific location within their orbital paths. Similarly, the behavior of 3I Atlas appears intrinsically linked to the prevailing solar wind conditions.
The cosmos does not offer us static entities to be simply cataloged. Instead, it presents a continuous display of dynamic systems engaged in perpetual interaction with their surroundings. Consequently, our comprehension of these intricate systems hinges upon capturing snapshots in enough diverse states to fully appreciate the spectrum of their behaviors. The Sun's own remarkable variability serves as a powerful demonstration that stability is, in fact, an illusion. Even when measured on the human scale of days and weeks, the electromagnetic landscape of our inner solar system undergoes dramatic transformations. If 3I Atlas possesses inherent electromagnetically reactive properties, if its constituent dust particles carry electrical charges, and if its structure demonstrably responds to magnetic fields and plasma flows, then its variable behavior becomes entirely expected. The truly surprising scenario would be one where it exhibited absolute constancy. This realization leads us to the culminating element of this conceptual puzzle, the one that unifies all preceding observations. For the themes of inherent variability, emergent complexity arising from seemingly simple components, and unexpected behaviors manifesting within systems, these are not phenomena exclusive to the realms of physics, astronomy, or planetary science. We are witnessing the exact same fundamental patterns unfolding within one of humanity's most rapidly evolving technological domains. The parallels emerging between artificial intelligence and fundamental scientific discovery prove profoundly unsettling in the most intellectually stimulating sense. This phenomenon centers on the 15th major debate surrounding emergent intelligence within frontier artificial intelligence research. During September, a significant breakthrough occurred when scientists developing next-generation physics simulation software observed something truly remarkable. Their investigation focused on training a transformer-based neural network designed to solve complex partial differential equations, mathematical frameworks that form the bedrock of understanding diverse physical phenomena ranging from fluid dynamics and electromagnetic fields to the intricacies of quantum mechanics. The training methodology employed a standard machine learning approach. Researchers presented the network with numerous exemplars. Here lay an initial condition. There followed a clear depiction of how the system evolved. The network's task was to predict the subsequent state. After extensive training on hundreds of thousands of these examples, the AI system began exhibiting behavior it had not been explicitly programmed or trained for. it started autonomously identifying conserved quantities intrinsic to physical systems. In the realm of physics, certain properties remain constant regardless of a system's evolution. Energy is conserved, momentum is conserved.
These conservation laws constitute fundamental pillars of physical understanding, yet they're not immediately apparent simply by observing a system's transformation. Recognizing them demands a profound grasp of the physics' underlying structure. Remarkably, the neural network detected these conserved quantities without any prior instruction regarding their existence, without being shown examples of conservation laws themselves. It simply observed that specific combinations of variables maintained a consistent value throughout the simulated evolution, and began leveraging this critical insight to enhance its predictive accuracy. This represents what researchers term metacognition. The AI learned not merely the specific task assigned, but the core principles governing the task. The network's capabilities then advanced further, demonstrating an ability to perform self-correction. The artificial intelligence system demonstrated a remarkable behavior. When its generated predictions contradicted fundamental conservation laws it had identified within its training data, it would autonomously modify those predictions. This adjustment occurred not because a programmer explicitly instructed it to uphold conservation principles, but because the network had independently learned that adhering to these physical laws significantly enhanced its predictive accuracy. In effect, the system was performing self-correction, debugging its own nascent understanding of physics. This capability ignited intense discussion within the artificial intelligence research community. Critics contended that this was merely sophisticated pattern matching at an unprecedented scale. From this perspective, the network simply detected statistical regularities within its vast data set and exploited them efficiently. They maintained there was no underlying comprehension, no genuine reasoning process occurring. It was purely the result of highly advanced curve fitting. Conversely, other researchers observed behavior strikingly reminiscent of emergent intelligence. They argued the system wasn't merely memorizing examples, it was extracting core governing principles, applying these principles flexibly to new scenarios, and critically assessing the consistency of its own outputs. Performing these specific actions, principle extraction, application to novel situations, and self-evaluation, are recognized as cognitive behaviors. This fundamental disagreement carries significant weight as it directly addresses profound questions about the nature of intelligence itself. Does authentic intelligence necessitate consciousness? Is biological origin essential? Or is intelligence simply the manifestation of sufficiently complex information processing regardless of the underlying substrate? Furthermore, can an entity exhibit intelligence without possessing self-awareness of that intelligence?
These are no longer purely philosophical musings. They have become critical engineering questions with tangible real-world consequences. Consider the phenomenon of emergence. This describes how complex, organized behavior can spontaneously arise from the interaction of relatively simple components. Emergence is demonstrably real. It manifests within artificial neural networks like the one described. It also occurs abundantly in biological systems, such as insect colonies or neural networks within brains. Moreover, emergence is evident within physical systems as well. Crucially, emergence demonstrates that achieving complexity does not inherently require pre-existing intelligence. It can arise from the inherent dynamics of the system's constituent parts interacting. True organization often arises without deliberate design. Under specific conditions, spontaneous order can emerge from apparent chaos. This phenomenon manifests physically. Minute dust particles, influenced by electromagnetic forces, can self-assemble into structured formations.
Similarly, charged grains within interstellar clouds naturally align themselves along cosmic magnetic fields. Electrostatic forces actively sculpt intricate patterns within ionized gases, known as plasmas, while certain chemical reactions generate striking oscillating or patterned behaviors. Crucially, none of these complex structures necessitate conscious minds or predetermined purposes. They arise solely from fundamental physical laws operating within regimes where intricate nonlinear interactions produce surprisingly organized outcomes. Titan, Saturn's largest moon, exemplifies this emergence within a planetary system. Its atmosphere and surface environments involve complex interactions between dust, ice, and various charge configurations. These components explore countless possibilities under the constant influence of solar radiation and powerful magnetic fields, gradually settling into stable, persistent configurations that maintain dynamic equilibrium. Neither cosmic emergence nor artificial intelligence require invoking traditional concepts of intelligence. Advanced AI systems represent emergent computation. Their neural networks are built from silicon and electrical currents running defined algorithms. Yet the sophisticated behaviors observed during training were not explicitly coded. These capabilities emerge organically from the learning process itself as the network navigates vast possibility spaces to discover effective solutions. Similarly, Titan's organized atmospheric and surface phenomena are not evidence of life. The Moon exhibits complex, structured behaviors, but these arise from the same underlying physical interactions that govern the dust and plasma examples mentioned earlier. Neither system depends on biological consciousness or purposeful design.
Both represent remarkable instances where profound complexity arises spontaneously from simple components interacting under specific physical conditions. The structured outcomes, whether observed in cosmic dust clouds, planetary atmospheres like Titans, or artificial neural networks, emerge inevitably from the fundamental rules governing their constituent parts. The journey from chaos to coherence, where the whole reveals properties entirely unforeseen by its individual components, represents the final, profound lesson of our exploration. This is the cosmos's ultimate lesson. It rewards genuine curiosity far more than complacent certainty. History consistently demonstrates this truth. Each time humanity has clung to a sense of absolute understanding, each time we've confined our vision within the boundaries of established theories, reality has inevitably revealed our thinking was far too limited. The revolutionary insights of quantum mechanics arose directly from perplexing spectral lines that defied contemporary explanation. The theory of relativity emerged from deeply puzzling observations regarding the nature and speed of light. The concept of plate tectonics itself stemmed from the remarkably strange fit of continental coastlines, a puzzle that challenged the static Earth models of the past. Crucially, none of these paradigm-shifting discoveries originated from a comfortable adherence to existing paradigms. They all germinated from the seeds of anomalies, those seemingly insignificant details that refuse to fit the accepted mold. Consider 3 Atlas. It stands as a stark anomaly, a celestial visitor that defies our existing categories, violently challenges our preconceived expectations, and fundamentally undermines our current models. Its very existence suggests the potential for emergent physics we have yet to recognize or comprehend. It might represent a wholly new class of natural object, one that forms under conditions entirely unsampled and unimagined within our terrestrial laboratories. Or it might be something else entirely, a phenomenon demanding we expand the very fabric of our understanding in ways currently beyond our imagination. Yet amidst this profound uncertainty about its origin, one truth remains absolutely inviolable.
3 Atlas is actively teaching us. Every single observation, every captured spectrum, every transmitted image constitutes invaluable data. This data speaks volumes about the universe lying beyond our solar system. It illuminates how matter behaves within the vast, complex dance of interstellar space. It offers crucial insights into what transpires when objects originating from entirely foreign cosmic environments enter our local neighborhood. Most significantly, it forces a confrontation with the acknowledged limits of our present comprehension and simultaneously reveals the immense untapped potential for future discovery.
Indeed, the year 2025 has proven itself a year defined by small revolutions within the scientific community. It has witnessed tantalizing hints concerning the elusive nature of quantum gravity. It has presented observations of impossible atmospheres around distant worlds. It has seen the unexpected expansion of our knowledge regarding deep biospheres. It has delivered solar surprises that challenged long-held assumptions. And it has revealed emergent behaviors in artificial intelligence that defy simple programming logic. Each of these developments reinforces the central lesson. Curiosity, not certainty, is the path forward. Each individual phenomenon might ultimately seem less groundbreaking than initially suggested, perhaps even dismissible. Yet when observed together, they collectively form a compelling portrait, a science undergoing profound transformation. We stand at a pivotal juncture where established theoretical frameworks are demonstrably reaching their limits. An accumulation of observations exists that stubbornly resists neat fitting into existing paradigms. Simultaneously, the foundational elements of the next generation of theories are quietly gestating yet remain unborn. Amidst this intellectual turbulence, there exists 3 Atlas, a startlingly green, luminous visitor from interstellar space. It fundamentally refuses to adhere to known astrophysical rules. It produces powerful jets of material despite the conspicuous absence of readily available gas. It emits an intense glow that cannot be accounted for by conventional chemical processes. It organizes itself with an almost unnerving symmetrical precision that seems suspiciously deliberate. This enigmatic object directly challenges us to find an explanation, while profoundly reminding us that such an explanation might necessitate entirely new scientific tools yet undiscovered. This experience transcends the mere study of one peculiar comet. It speaks to the very essence of scientific inquiry itself, how we approach the profoundly unknown, how we navigate the delicate balance between healthy skepticism and necessary openness. That is a crucial reminder that the universe holds no obligation to conform to human expectations or make intuitive sense. Our cherished theories represent mere maps, not the vast and complex territories they attempt to describe. Every map possesses inherent edges, beyond which lies uncharted territory, unmapped and unexplained. 3 Atlas currently resides precisely at that unsettling frontier. It occupies the unmapped space where cometary behavior defies established norms yet occurs nonetheless, where purely natural explanations strain to provide coherence, yet plausible artificial origins seem audacious leaps, where every proposed answer invariably spawns a cascade of even deeper, more perplexing questions. This state is inherently uncomfortable and frustrating.
Yet, paradoxically, it is precisely within this charged zone of uncertainty and unresolved tension that the most fascinating and potentially revolutionary scientific discoveries are most likely to emerge. So, what exactly is 3 Atlas? For now, we remain genuinely uncertain. The possibility persists that, despite our best efforts, we may never achieve definitive, certain knowledge about this extraordinary interstellar traveler. It continues its journey away from the Sun, gradually dimming as it heads back into the interstellar darkness from which it originated. Within a year or two, it will become too faint to be observed, except by the most powerful telescopes. The opportunity for study is fading. Whatever secrets it holds may depart with it. Yet it has revealed to us something significant. It has shown us that the universe still harbors surprises, that interstellar space is not empty, but populated by objects that we are just starting to catalog, that our solar system occasionally receives visitors that defy anything we have previously encountered, and that the next visitor might be even more extraordinary. For 3 Atlas is not merely a visitor, it is a reminder that we inhabit a cosmos brimming with phenomena yet to be discovered, with physical laws yet to be formulated, and with possibilities yet to be imagined. It is a reminder that the universe is vaster, more peculiar, and more engaging than our theories propose. And it is a reminder that the most appropriate response to mystery is not dismissal or hasty explanation, but careful scrutiny, meticulous analysis, and the readiness to be astonished. We are positioned at the threshold of discovery, not because we have uncovered conclusive answers, but because we have encountered questions we never knew how to frame. 3 Atlas has posed them for us, and whether it is unveiling novel physics, introducing new categories of objects, or presenting something for which we lack terminology, the dialogue it initiated will persist long after it disappears from our telescopic views. True scientific advancement rarely marches forward on a path paved with absolute certainty. Instead, it is forged in the fires of profound curiosity and the audacious courage to confront the vast, uncharted territories of the unknown. It demands a deep-seated humility, the willingness to acknowledge our limitations, to admit we simply do not grasp the intricate workings of the universe. It requires the intellectual fortitude to dismantle cherished models and theories when they prove inadequate, replacing them with new frameworks born of relentless observation and persistent questioning. Scientists must continually push against the boundaries of our current understanding, not ceasing in their efforts until those frontiers yield a fraction of their secrets. It was precisely from beyond those very boundaries that 3 Atlas emerged.
This enigmatic phenomenon, originating from the mysterious realms between stars, made a fleeting yet astonishing passage through our solar neighborhood. It revealed wonders to us, phenomena so extraordinary that our minds continue to grapple with comprehending their full significance. Though it will soon fade back into the profound darkness between the stars, 3 Atlas has bestowed upon us something of immense value. It has imparted a crucial lesson, that within that vast cosmic void, hidden from our initial expectations, exist entities and principles that fundamentally challenge our established knowledge. This encounter serves as a powerful reminder, a clarion call to why we first gaze upwards at the night sky. Our pursuit is not merely to validate the theories we hold dear. The true exhilaration lies in the unexpected thrill of discovering that our understanding was incomplete, perhaps even profoundly mistaken. There is a unique joy in realizing the universe possesses a strangeness and complexity far exceeding our most vivid imaginations. And there is the singular privilege of witnessing something truly unprecedented, something that defies existing categorization. Regardless of its ultimate nature or the secrets it may conceal, 3 Atlas has granted us this privilege. This interstellar visitor, exhibiting characteristics that stubbornly resist explanation, embodies a paradox that refuses to crystallize into a neat resolution. It represents a mystery that deepens with each new observation, each carefully gathered data point. Its presence grows ever fainter each passing night as it retreats further into the cosmic dark, carrying its profound contradictions back into the depths of space. Yet it remains, irrevocably changed us. We now wonder with renewed intensity. We know with absolute certainty that the universe harbors countless more stories yet to untell,
holds countless more surprises poised to be revealed, and conceals innumerable mysteries lying just beyond the edge of our current comprehension. Thus, this state of affairs is precisely as it ought to be, embodying the perfect alignment of circumstances and intentions. It reflects a harmonious equilibrium where every element exists in its rightful place, contributing to a larger, intricate design. This outcome is neither accidental nor arbitrary, but arises from a deliberate balance of forces, ensuring that all components function in seamless unity. Such a configuration underscores the inherent order underlying apparent complexity, revealing how interconnectedness fosters stability and purpose. Consequently, this arrangement not only meets expectations, but transcends them, illustrating the elegance of things falling into place exactly as they should.